Same issue. We could do map of the moon probably a few days. Literally no way to transform it under half a year or a year. So pretty much there's so much data. So you have to do pre-processing, you have to analyze it, you have to reduce it because otherwise your satellite will cost 10 times less than actually your data center budgets. So data transmission is a huge, huge, huge problem. And the question also is that you want to add it inside of the camera. Why do you want to do it inside of the camera? Is it allows you to combine the knowledge and do this, get most of the hardware. So you could transform it outside the system, inside of the more specific on-board computer, but when you do at least cascading models inside of the camera, reduce the system data load, and you can kind of use the knowledge of the camera builders, because kind of there are different domains, and you can use some specific camera development knowledge already building the models and obtaining the models when you make the purpose-built inside of the camera. So a bit of the background. So where are we? How's it going? So ideally, how you build your typical camera. You have your sensor, you have the splits of the camera interfaces. You typically split the control interface and data interface. Data interface, you have the front end, which is you get your MIPI signal, you get your pixels in, you try to get this sensor abstracted, then you have an image-based processing, grooming 10 pixels, uniformity correction, a bunch of other start as well. So pretty much the first one, front-end goal, get the pixels in, image processing goal, kind of standardized, normalized image. And then what typically happens is you pack it and ship it. And when it's gigabytes of data, you set format. So that's the typical. Then when you want to do is when you add this kind of model engine or AI engine, are we talking about? So there's like multiple options. You can go for high-level architecture-wise. You can go for NPU, so neural processing unit, or you have a different system chips, or you also have like external engines. So what we have is actually you get multiple things. Firstly, you keep this when we're talking about moving data. So when you're talking about moving data inside of a chip or inside of a closed hardware solution, then you can move data there in terabytes per second internally. So you start moving outside, you're typically talking about gigabytes per second. So that's the first one. So you can start moving data internal systems to a specific space where it makes sense to do specific image processing parts. What it means, you can kind of split those models apart and put part of the image pre-processing, which is model specific already, it's an FPGA part, and you, for example, something that's easy to accelerate, you can put in an NPU part. Absolutely nightmare in software architecture, and no tool supports it, but you can get really amazing performance out of it. Secondly, why the basic image processing and the model kind of acceleration start to work together is that typically you want to optimize for false positives, false negatives, and the percentage, like what is the certainty you kind of find some object or find something there. If you have really well built in coherent basic image processing and model acceleration, you can quite a lot improve performance. So what it means is that when you route the pixels and you have this sensor calibration that's really specific and you're known and you kind of know the degradation. Because if you're talking about really good scientific space sensors, then you are also taking account the degradation of the sensor inside of the basic image processing point. You can be updated, it can be tracked, you can take it all account in the really early phase. And this allows already you to remove quite a lot of error sources that they use for your typical CNN or RCN. And like, the good thing is you get a lot more out of the system. So kind of quick putting everything together. Like we are not final yet, so it will take us a bunch of time to finalize the product. But here are the quick takeaways which I can share. So firstly, you can actually get to extremely good performance results, way more than you would get putting those systems on. As I mentioned, stable preprocessing helps to improve the performance. You get quite a kind of reasonable power usage. Thinking about those small systems, of course it takes more power than the camera, but you still get a reasonable power usage. And for the clients, it actually is a simplified interface. But there's a bunch of bad sides as well. So what happens is all the issues that come from the early adopter. So these technologies are deploying in age models is nowhere near complete with standard system. So this one is still a lot of early adopters issues. Underlying system change, you get a performance jump sometimes, but you have to start from scratch. A lot of, let's call it, documentation by code. So a lot of information gets written by code. Unfinished interfaces, and what's the most the hard one always is that if you get off of the happy path, so if you want to do something specific for you that's not the happy path, welcome, you just create yourself a new PhD position and a research project. Absolutely interesting. Budget-wise, nobody's going to like you. And it's a way more complex product than it's that would be just a camera or just as a processing unit. But internally, by the end, you actually get way more out of it. So hopefully you can share more information in upcoming years as this product gets its first launch this year. So let's see how it goes. Thanks. Any questions? Go first.
Have you any solutions for infrared cameras?
We have it on the road not to integrate infrared camera and the video camera. I cannot talk more, but yeah, we have it on a pipeline to interface it and actually do the sensor fusion before it, kind of feeding it into the model. So answer is yes. Ask me in 6 months.
Okay.
So are you able to expand a little bit on the radiation hardening part? Have you looked into it? Because my naive mind would think if you're putting more processing on the camera head, you're going to have to work harder to make sure there aren't pictures and stuff.
Oh yes. Oh, it's tremendous work. So pretty much you have to the error correction. You have to do configuration. RAM needs a separate check. You have pretty much scrubbing all the time. Different memories going around. So other redundancies. But again, mostly it's a kind of it's called simplifications. So you cannot lose the configuration. You cannot lose your boot images. So some things are really important. But at the same time, you have, let's call it, when you have this continuous feed of image, you don't consider one image is kind of perfect truth anyway. So you can, if you build around it system, you can make it in such a way that you don't care if you get some losses to the running data. So when you have this running feed of image pipeline, so you kind of accept that there are some bitflips there and errors, just by thermals and other kind of how the system and sensors work.
Maybe also from the processing side, do you like for the processing consider, let's say, continuous image taking, so more like a video processing type of thing, or is it more to have, assume you get an image, I don't know, let's say every minute, just as an example, where you know that pictures might not be really delayed much anymore.
So both actually. So because you need both. So in some applications, when you're talking about SSA, you actually need a kind of continuous feed, especially when you're getting close. Once you see your object, or when you're doing this kind of, let's call it space scanning, you want to see like, hey, there's something new popping up. So it's like a basic object detection. In some cases, when you have like more of a still image, you just want to perform like a low FPS, like really once in a minute or something. Honestly, on a product perspective, you have to do both. But on a software firm architecture way, it's a complex. You sometimes need to switch out the models to do like switch between them, which is great also, always a risk. But so far we haven't found a way not to do it. So it's something that's it's not there, but we haven't looked into it. I think that's you cannot over it. So we should have to. And okay, and in other cases, sometimes, in some cases you need it, sometimes. Yeah.
As a customer, how much influence would I have in implementing own pre-processing steps in this MPU? Is it like a user request to you and you would do it, or is there the possibility to?
So pre-processing, we are kind of really not sharing like this is more fully us. If it's already like model side, then there's a collaboration. Okay. Because models typically are especially in space, are really application or mission specific.
That's why I'm asking.
Yeah. So then it's a collaboration or fully done by users, because like, one of the big problems is. Which actually goes for both space and defense, is that there's not a lot of training data available. Nobody is willing to share that, so and so it's more about a combination of we kind of helping to edge deploy or optimize the model that a client already has. Okay, thanks.
So, hello everyone, my name is Jānis Šate and I'm CEO of the company Vidlife Technologies, and today I will share some insights and results of our project, man-made modular front-end electronics for Earth observation payload applications. A little bit about background. This is ESA-funded activity. We are working together with, in consortium with TNO, a research organization from Netherlands, and the objective is to develop modular front-end electronics that supports different image detectors. They are listed in both hardware and firmware. And the target is, in ESA terminology, elegant breadboard. It is not a final product, it is TRL5. And about the motivation, there was ITT from ESA, and the main idea is that when you are developing imaging instruments and you are interested to use some new image detector, you have to develop custom front-end electronics for readout, for pre-processing, for everything. And then you have to prepare all the documentation, verification, and all the long work with a lot of risks, and it is very time expensive. And the idea from ESA and TNO was that all image detectors have some commonalities, like the LVDs, data lines and clock lines, they are similar. The power supply lines and power supply requirements, the ranges are similar. And the idea of this project is to introduce architecture level reuse. So what does it mean? This mermaid concept is that we have like standard front-end electronics, and for every specific image detector, small board of proximity electronics is developed that adapts the image detector interfaces and requirements to the front-end electronics. So in such case, all the work is not about developing unique front-end electronics for each image detector, but it is about minor work for only development of proximity electronics and also for verification and validation only for small part for each new design. And this is the main idea we are trying, exploring, and introducing into the hardware. And here is the top-level architecture of such system. It comprises two parts. This part is high reliability part. It is a microcontroller-based part that oversees the whole system. It controls the power supply lines for image detector, for the processing and FPGA, and for sure for itself. And it provides all the memory scrubbing, anomaly detection, all the management of the system. And then there is a separate part. This is a high-performance unit part. It is FPGA-based part that provides image readout and pixel processing and image stream out. The main interfaces of the design is here is like custom LVDS-based interface for the image readout and control, and also for power supply of the image detector. The image is streamed out via gigabit Ethernet, and this microcontroller part is controlled by CAN bus interface. And the project demands that here are three variants of the front-end electronics. I will explain it later, but there is COTS components of the shelf variant, radiation-tolerant variant, and radiation-hardened variant. But the main requirement is that all three variants are hardware, firmware compatible, and form factor compatible. And for sure, this front-end electronics reuse, it is not only about the hardware compatibility, but also about the FPGA firmware compatibility. As we know that FPGA firmware development is very time expensive, and if you have to develop specific firmware for each new image detector, it increases the development time a lot. And so we have a modular architecture, and there is only one module that needs to be changed if you are changing the image detector. It is the image detector readout controller, and the rest of the system is the same for all image detectors. And the architecture is quite simple. Here we have the image detector readout. We receive the pixel stream. We have specific module of pixel operations. I will explain it in the next slide. And then we are buffering all the pixels in external DDR3. Then there is compression. If you want, you can use the flash memory for non-volatile storage, and then there is a gigabit Ethernet IP core. And all this system is controlled by the soft-core CPU. We have RISC-V soft-core microcontroller for it that supervises and manages all these modules. And the most complex part is the pixel operations. Those are very basic pixel operations required by the project and like common imaging instrument needs. By default, it provides for operations. It is windowing, ROI selection. Then there is the passive damaged pixel correction, background subtraction, and binning. All this firmware, especially in this module, all firmware excepting damaged pixel correction is developed by us, since we are company focused on FPGA firmware development. But yes, and how this processing goes, all the incoming pixel stream at first is buffered into the external DDR3 memory, because it reduces the risk that the pixel stream, the data rate is quite high, in the gigabits, as the previous presenter said. And there is a risk that this pixel processing could not support the full frame rate. And so we can reduce the frame rate by buffering. But for frame rates like 20 frames per second for all image detectors we are planning to introduce, we can support. And for sure about performance, usually everyone asks what is the power consumption. I guess it is one of the main questions on FPGA-based processing systems in space. And it is assessment based on typical typical current values, and the FPGA modeled FPGA power consumption based on the estimated utilization and the junction temperature at 70 degrees Celsius. And in our design, we have 3 power supply lines. We have a power supply line for the image detector, and it changes according to selected detector. Here is the list what are the supported for the first design. And for this front-end electronics, the power supply, power consumption is more or less constant. For the microcontroller board, we expect that it will be like 3.75 watts and a little bit 4 watts for the FPGA board. But yes, the design puts some requirements on the heat management, since the thermal runway of FPGA might be quite an issue, since if the junction temperature would increase of the FPGA, the power consumption will be increased exponentially, and it can be like a really bad process without proper heat management. So this is always why we see a minor risk in that how much pixel operations and processing we can put on the FPGA, but because it increases the demands for the heat management, and it should be always considered by our opinion. And the next one about the system throughput budget, because the peak data rates from the image detectors are quite high. They are from 1 gigabit per second up to almost 10 gigabits per second, and it should be mentioned for the CMV to 12,000, we are expecting to ensure only 25% of the frame rate, because this image detector is quite big. But we can handle such the peak data rates. We have quite small external memory bandwidth. We have, for simpler design, we have only one DDR3L external memory, 8-bit memory, and the FPGA limits the transfer rate to such number, and so the theoretical peak rate is around 20 gigabits per second. But what does it mean? We can ensure that we can stream out the maximum peak, maximum frame rates from each detector and store them in the external memory and then process it in the slower rate. But for example, what we cannot do like, let's call it real-time processing if we are wanting to store and read in the same time in the external memory. As we can see, for some image detectors, we only have like 10% access time for reading if we are writing with full frame rate. But for the initial design and for this elegant breadboard design, it is good enough. And for the future designs, we can just put the second DDR3L memory at the FPGA interface, and a lot of problems will be solved. About Radiant's toleration strategy, these are requirements from ESA. The main idea is that we have 3 designs, component off the shelf, so all the components are COTS, and it is for lab prototyping. It is a cheap version for testing and product development. Then there is a radiation tolerant variant. What does it mean? It means that there are specific requirements regarding single effects and total ionizing dose, and the microcontroller part is designed by space-grade components, while this FPGA part is still by the commercial components of the shelf. And the main idea is that this should be like a variant for the new space LEO missions. And as you can see, the radiation hardened part is that it is the most expensive variant, and all the parts are space-grade parts with certain radiation tolerance parameters. And where we are right now, currently we have developed the designs, PCB designs and FPGA firmware designs mostly for all 3 variants, and only COTS variant, components of the shelf variant, will be manufactured. And here you can see the both boards. This is the FPGA board, high performance unit. It has 2 interfaces, one for image readout, one for control. There are debugging support, and for lab use, gigabit Ethernet. And here you can see this microcontroller part. It is based on engineering models of the space-grade components, and it has CAN bus interface, and here is a stacking connector to put both modules together, as you can see here. And we expect that the system bring up and the validation will be completed until the June, July this year, because currently it is under manufacturing and we are just waiting for our systems. And for conclusion, the main idea of all this design is to isolate the detector-specific complexity on these proximity electronics boards and to ensure unified hardware and firmware that is compatible with specific list of image detector. And we have explored a lot of issues regarding the performance, power consumption, and the design, and transferred it to the architecture and to the hardware that is currently at the manufacturing. And towards what we are going to do, it's just a development project. We will receive all our boards. We foresee there will be issues, there will be delays, and a lot of struggle to bring them up, to run all the validations, and to test them with some image detectors. But for the more far future, we see that we can increase this system to add additional detectors and to develop it to the higher TRL. And regarding to the collaboration, speaking honestly, we are not open for hardware development collaboration, but we are more or less a FPGA firmware development company. And if you are interested in firmware development for image, for cameras, or some imaging instruments, especially for some basic pixel operations like binning, filtering, error correction, or just some baseline system integration, we are open for collaboration, and we can develop that type of designs or specific IP cores. This is what we are doing on a daily basis. So thank you for your listening, and I'm ready for questions. Yes, please.
What type of FPGA are you using?
Yes, Palaver from Microchip. Yeah. Yes.
So you mentioned, I don't know if I got this right. Your DDR is on the reusable part of or the modular part, not on the specific content, right?
The DDR?
Yeah, I'm just wondering, like, if there's a specific size that you already conditioned for all the detectors you plan to use, or is it more open to, because if you put it on the design specific, then it's a little bit more open, I guess, for the detector. But if you put it already on this module, then you're sort of constrained, I assume, if you need like a more data-heavy detector later. And how much memory do you think?
Yes, so the DDR currently it is in this reusable part of this hyper FPGA board. Currently, it is rather limited to move to push design further, and it is quite small. It is 8 gigabit, but once this architecture will be validated after the manufacturing and all the processes, we expect to increase the size. Yes. Currently, it's just 8 gigabit, 8-bit DDR with certain constraints. It is limited. But it is easy to implement, and there are some other issues. We have to pay attention that it is ESA project. We have to use ESA IP cores for DDR interface, and also these IP cores have some constraints, and all this comes together, and so we came up with such baseline solution. Yeah.
About the form factor, is this defined by ESA, or is it based on like the standard you already follow, or is it how? Because it's a very square, yeah. But is this?
Yes, it is defined by ESA, and the main idea it's more or less 10 by 10 centimeters. It's like in the ITT it was written it should be smaller than CubeSat form factor. Actually, it is a little bit bigger, but for this elegant breadboard, TRL, it is enough, and he's agreed, so we can continue. Because we have to implement some debugging interface that will not be in the final design, but currently when this validation will be there, we have to put some overhead in the hardware to reduce some development risks. So thank you everyone.
Yeah, it's fine with me. I just thought like there was another important. Yeah. It's fine. Do you hear me, guys? And I don't need to carry the microphone. Okay, it's easier, I think. All right. Yeah, I'm here. I'm presenting today the Plato project, specifically the data processing system. And I'm from DLR, as you can see. So what I show you is just to give you a quick overview of the Plato mission itself and its science objectives, then what is the current state, to give you a feeling of where we are, show you a bit about the payload architecture, and then go into the actual data processing, and especially also the AIT, because that's my responsibility. So for the Plato mission, it's one of ESA's M-class missions in the Cosmic Vision program. It's basically an exoplanet mission to detect Earth-like exoplanets around Sun-like stars in the habitable zone. So basically we're trying to find Earth number 2 somewhere out there. We're using the transit method, basically visualized below there. I guess most people know it, the principle behind it. The general idea is to have at least a 4-year observation phase, so to have an extended phase of long observation of a lot of stars, with a large field of view, meaning more than 2,000 square degrees of instantaneous field of view. If the decision will be in the future to also look at different field of views, then of course the complete field of view will increase. And the idea is to basically just generate an enormous amount of data set, basically a large catalog which can be used by scientists in the end to detect planets. The science objectives are basically to determine the properties of planets, of course, and see how planetary systems evolve, but also to correlate see if there's a correlation between the properties of planets and their stars. Then there's a question whether there's a dependence between how many Earth-like, so terrestrial planets there are, and their formation environment. And then lastly, also identify targets for later close-up observations, which means mostly looking at the atmosphere with a spectroscope. The current status is quite nicely, so the picture is just from, I think, 2 months ago, actually. I don't know why it says in the link 2023, but it's actually 2 months ago. That the satellite is integrated, so it's currently in the preparation for the TVAC campaign. The whole environmental testing is ongoing. In the software, where I'm responsible for, we're in the final phase, so we're implementing the final features and starting the final testing campaign, which means the functional and performance testing is ongoing or just started, and we're working towards the software qualification review right now. So basically, trying to provide or produce the input for the software qualification. How does the payload look? Schematically speaking, we have, in the first place, we have the central unit, which is the instrument control unit, which is basically there to, as the name says, control the instrument as an entire thing, and to provide an interface towards the spacecraft. Of course, also compression is. Then there's the main electronic units, which is, as also the name suggests, the most important part. It controls 12 telescopes which are on the satellite. and reads out the data from the 24 cameras, sorry, 24 front-end electronics. Then we have the fast electronic units, which does the same job basically for 2 special cameras. So there's 24 normal telescopes, which are read out every 25 seconds, and there's 2 cameras which are read out every 2.5 seconds. And the reason for that is that they also provide the input to the attitude control system of the entire satellite. So in the Plato mission, the payload is also involved in the attitude control of the entire satellite, because otherwise the attitude determination precision wouldn't be high enough of the satellite itself. And then lastly, we have the fast ancillary electronic units and the normal ancillary electronic units, which is basically just to give a time synchronization baseline for the entire system. So as we have in total 26 cameras, the timing between all of the different cameras needs to be controlled very well. Otherwise, we would have very high data peaks at certain amount of times, and at other times there would be nothing happening. So to not overstress the system, basically, there is a very precise timing between all the different cameras to sort of spread out the readout of all the cameras in time. Now to the software side of everything. We start again with the ICU. There's in total 5 software components, starting with the ICU boot software, which just handles the ICU internally and just basically gives a very basic interface, more or less, in fact, for a safe mode. It's really just to have an interface with the spacecraft for the payload. And to boot the ICU application software, which then handles basically most of the payload, as you can see. So it handles all the timing units, it handles all low-level functionality of space-wire routers and power supplies inside the entire payload. And also is again the interface towards the spacecraft. So it provides the housekeeping data, but also the entire scientific data is transmitted from the ICU towards the spacecraft. Then there is the NDPU application software, which is the main, let's say, scientific software. It does the most scientific data processing and handles the readout of the 24 normal cameras with the 25 seconds cadence readout. And then lastly, we have the FDPU init stub, which is a very, very just 2-digit number kilobyte boot software, which is really just there to have an interface to actually boot the FDPU application software, which does the handling of the attitude data. So it handles the 2 fast cameras, and it handles or calculates basically attitude information that is then provided to the spacecraft attitude system again. Yeah, so that's the whole payload. So now we look into the data processing. So as we heard before, data processing is a complicated thing for the whole payload. As we've just seen, we have 26 cameras, so the data volume would be again way too high if we would transmit all the raw images. So the first step, as was also just presented as well with the front-end electronics, what you do is basically a windowing step where you already just cut out the pixels that you need from the CCD. This is also done in our case in the front-end electronics directly. In the normal case, there are some different cases, but in the normal case, this is just 6x6 windows. So meaning 6x6 pixels, because a star normally is spread across 4 pixels, and that's it. So that's let's say how good the pictures are. Then this is the part of the NDPU application software, and as I said, it's doing the main scientific processing. Sometimes for a very small number of like windows, it's just routed through. There's nothing really done in processing except for correction mechanisms, so getting rid of dead or hot pixels and things like that. But then there's also the calculation of the light curves. As you've seen for the transit method, you basically care for the light curves of the stars, and that's already done on board because the light curve information is a lot smaller than the actual image data, of course. And then there's also centroid data, which basically means just X and Y coordinates, where is the center of the star in the image, which also reduces the data amount already substantially. For the F side, we have the FGS, which is the guidance system processing, which basically from the whole image data then calculates down to a single quaternion, more or less, and some time data. Yeah, basically 4 quaternions, 4 quaternion components, and that's the information that's coming out there as well. So to also just reduce the amount of data again substantially. And even that was not enough to reduce the data yet, so all of that is still input into a hardware compressor inside the ICU, which then forwards the whole data into the spacecraft. From an AIT perspective, what we have in our facilities in Berlin is basically the hardware in the loop test setup. It's a reference test bench where we don't have, let's say, all the units as in the real satellite. We already have some units missing. As you have seen, we have several units which are in there twice, but we only have everything at maximum one time in our setup due to cost reasons, of course. For the test bench, we use the EQMs as much as possible, and it will be the reference setup for the payload-related activities for the coming years, so also for the entire mission duration while the satellite is flying. Basically, all the operations will be tested upfront on the test bench in Berlin before it's actually going to be uploaded into the satellite. To give you a rough feeling of how things look in reality, as always, we have a lot of shiny boxes, so that's the unfunny part about developing software. In the end, it's just shiny boxes or black boxes, but a lot of cables. So we got at least to play around with a lot of cables there. And yeah, it's for us at DLR, it's also one of the biggest projects we had so far, so we had quite a learning curve of how many cables there can be. Actually, that was really an eye-opener. Yeah. To do the whole verification of the software, we of course developed a test data archive, because so in full nominal science mode, Plato will produce a bit more than 400 gigabit of data per day, compressed 400 gigabit data per day. So we also, for our final tests that are coming soon, hopefully, we need a data archive where we can store all of that. And the idea is that we have the TSC, which is sort of an automation tool for testing from Therma. We run it through the archive, and then we have our unit under test, which in our case is the entire test bench. Basically, everything is running via Ethernet, so we have simply a TCP protocol and can just sniff into the Ethernet data stream, which we then basically divert as well to a Kafka queue, which gives us the flexibility to spread out the workload among different computers. Because Kafka is a decentralized data queue system, you can share the load between different computers to make also for the EGSE setup the processing requirement a bit lower per unit. This is then stored into a PostgreSQL database, which in the end is just to store a big hard drive, of course. And at the same time, we also provide the TMTC database, of course, for the entire payload. And we use that database in the background also to basically pre-process all the data that's coming from the payloads during our tests, to store not only the raw data stream, but we continuously process this up to the telemetry parameters, which are calibrated to engineering values, and store basically all the steps in between with enriched metadata. So when was it received, to give it a UUID, just to be able to track everything in the whole system. And then basically on the other side, we have the two steps, which in the end is Python accessing the PostgreSQL database, where we can then actually do the post-processing, because as you might imagine, during the live tests, you can only check, let's say, a very limited amount of parameters directly, but the entire amount of data forces you to do a lot of the checks that you want to do on the correctness of the data in the aftermath. So you just cannot do that live. And for that, we simply use Python because, well, it's simply easy to use. For the documentation and reporting, as you might imagine, we're an ESA mission, so documentation and reporting is a thing. Everybody knows. We don't need to go down that road, but anyway, we decided to make our lives a bit simpler and develop a system where we say that our test scripts are actually the single source of truth, meaning if anything comes down to what did we do or what happened, we can always go back to the test scripts and also create our documentation, at least to a large extent, out of the test scripts effectively. And what we're basically having is a test framework where we have a sort of test proc mode, which means we can produce our procedures directly from the test scripts as well. So we don't need to write a procedure, then implement a test script, and then run the test script to write a test report and everything, but we write the test script in the beginning, and from that we produce the test procedure, actually. And as you can see, that it's sort of an HTML format. It's not very nice looking, but it gets its job done. Then we have the sort of normal mode, which actually means we're executing the test. So it's run on the test bench. The test proc mode you can run locally on your computer or anywhere, that doesn't really matter. But when you run the normal test mode, of course, you need the test bench to actually see the data, and you see, you see that there's basically telemetry being, telecommands being sent and telemetry being received. Or you can have it in an error case, you get a red highlight and say something is missing. To make our lives a bit easier there. Then out of that we have a report generator, which actually transforms it into a more manageable Excel format. These are last Excel, so we do Excel. And it helps basically in showing the major steps, let's say. There is not anymore the entire test data in the background, but basically step by step it shows what has been done and was the test passed or not. And since we're also doing, of course, verification with the whole test campaign, we need to prove to ESA that we've seen all telemetry and all telecommands. So we have a Python script again, or in the case it's a Jupyter notebook, that basically takes the HTML test reports and generates the TMTC coverage to show us which telemetry commands have actually been sent and which telemetry has been received. But we can also run them simply with the test scripts to show, okay, if we would run the test, which telemetry would we see and which telecommands would we actually have sent. To already see our coverage, what we would see if we were actually running the test. And that actually helps in planning the test activities, because you know up front, roughly at least, what you will be seeing already. And the same then goes for the verification control matrix. We can also run that actually on the test scripts, or later on the test reports. Also again to either see what would be the coverage if we run the test, and if we actually did execute it, which requirements have been verified and which not. And to achieve the last step, we actually also, I think it's not really visible here, no, unfortunately not, but we also track basically that each requirement directly in each test step, which will be verified by the respective test step. So also the test scripts basically have the direct correlation which test step verifies which requirement directly. So again, it's stored in the test scripts. And we have in the background GitLab, as you might imagine, so we have also version control, and we know what we did basically for the entire pass. And a little bit more about the verification control document, because as you've seen, we have several software components coming from different partners. The whole verification topic is also getting a lot more complicated, so you don't have just a single software or a single component that you're verifying, but we have basically requirements that apply to either all of the software components or just some of them or just a single one. So we started to develop, again in Excel because it's easy to handle for ESA, we started to develop a system where we have basically the applicability of a software requirement to each software component. We have a column basically for each software component where we say what was the actual evidence for the verification activity, either if it's a review of design, for example, we have which document, or if it's a test, we have directly generated from the test scripts again. We have which test scripts have shown that the requirement was verified. And yeah, basically it's filled from the things that I've shown before from the tools automatically. Of course, not for the review of design where you actually need to go into the documentation. That is still manual work. And yeah, as I said before, we basically can use the test proc mode run to show or to plan already and see how much of the requirements did we cover or would we cover if we run the test. And if we then actually execute the test, we see as a verification evidence in the test report what was actually, first of all, what was tested, and most of all, what was tested positively. So what did actually pass and what failed. And then this whole thing, because of course if you want to do requirements engineering properly, it can then be imported into Doors again. So there is a simple import script that basically tracks it back to our original requirements database. So in conclusion, It's a complex software system. We have many software components. They're actually not all developed by ourselves. They're also from European partner institutions. They're needed to create such a big system, but that also includes, of course, the problems of having, especially in Europe, many different cultural backgrounds, many different people being involved, at least luckily not different time zones. That's already a good start. The main challenge of the whole system is data reduction. So as we've already heard before, imaging sensors create huge amounts of data, but we simply cannot downlink them. The whole testing thing is complicated because we have, as you've seen, a complex test setup and a lot of software functionality that we need to cover. So automation is key, and I think that also applies for everybody, as you've shown before as well. Testing complicated systems is not possible anymore today in a manual way. And verification is complicated, as you've seen with the different software components. There is just a lot of things to verify. That's it. Are there any questions? Yes.
Is there any reason why you use PCL for the test scripts?
Because the tool from Thelma, so the TSC, actually uses Tickle as the programming language. And we can quickly go back from the screen here. So basically, this is what was provided from ESA to us as the spacecraft interface simulator, which basically provides the power interfaces for all the payload units, and that has integrated the TSC already. So we're bound basically to the TSC. It does its job quite well. The only caveat is you have to use Tickle in the end. Any other questions? Everybody wants coffee, I guess.
Okay, I will have one question.
Yeah.
You mentioned about the verification also of the software modules. Regarding the FPGA firmware modules, ESA is suggesting to use UVVM framework or something. Are you using specific FPGA verification frameworks, or you are making all like in-house developed?
So for the Plato project, actually, we didn't do the FPGA development, luckily. So there we didn't really care, let's say. For our new mission, so I will have another talk tomorrow in the evening. I won't present much on the FPGA, unfortunately, because I'm not the FPGA expert. But there is currently the discussion ongoing how we will be doing that. So far, the previous missions were actually quite simple, so it was more or less doable without a framework needed in that sense, because the functionality was very simple. We were in very complicated FPGA designs, but that will change to some extent for the future missions. And there we also want to sort of interweave basically the low-level software development with the FPGA functional verification activities. Because of course, the things you need to do to verify the FPGA functionality can be used as, let's say, low-level drivers for the software already. So that's an interesting approach we're trying there, but it's still not fully defined yet. That's the idea. You're welcome. Any other question? Yes, no? Is there another presentation coming? Yeah. Okay.
Is it PDF?
Yeah.
Can you full screen?
Yeah.
Ah. Genius. Does it work with the clicker?
Yeah.
Oh, no.
How do I get it?
Ah, great. I can go back to that.
Yeah. One.
I have to press this twice to go back.
Yeah.
And this is the later one?
Yeah.
Ah.
Yeah.
Excellent. Okay. So good morning, everyone. I'm Eric from from the Norwegian, and I'm a PhD candidate at the Norwegian University of Science and Technology at the Small Satellite Lab, and I'm going to talk about cloud avoidance for agile small satellites, so satellites that can move a lot, using onboard processing. Okay, so what's going to happen? Oh, it's nice cut out. First of all, I'm going to give you a bit of a motivation. I'm going to show you a typical mission profile that we have with our satellites. Then I'm going to give you a high-level overview of what I'm actually trying to do here. Then we're going to go a bit more into detail of the dynamic pointing architecture or the pipeline that I'm developing. Then some challenges that I'm facing and I'm going to face, I suppose. And at last, a quick summary and future work, or what's the next steps. Okay, so I'm going to start with the typical problem. You have an expectation, and then a reality comes in, and your expectation is shattered. We have two satellites, HIPSO-1 and HIPSO-2. Currently, how we operate them is that we schedule on-ground observation targets, and then check for cloud coverage for each of those targets to see if we want to capture or not, because we don't want to take pictures of clouds. And then we perform the imaging using our hyperspectral imager of the target. And wait. So what you can see here on the right in this graph, we have here the measured cloud cover, and we have here the expected cloud cover. And usually there's a lot more clouds than we actually expected with the weather forecast, because we schedule our captures 3 to 4 days in advance. And as you all know, weather forecast is not the best. So if you try to say, oh, in 3 days there is not going to be clouds, it might be wrong. And we observe a lot of this. And this is very annoying. So what can we do to prevent this? Now, what do we actually do with the HIPSO satellites? They're mostly used for algae bloom detection and classification at some point. So we look a lot at the oceans, especially at the oceans in the far north, which can be very cloudy, as you can also see here on the right. So here, you can see there's a bit of an algae bloom going on, and there's also a lot of clouds. What's really nice though about algae bloom, so this is a huge area. Here you would see the coast, here is Norway, and Russia is here. So this is an area about 400 kilometers in size. This algae bloom is huge. It was in August 2025. And we don't really care what part of the algae bloom we image, as long as we image some of it. So we could image this, we could image this. We just don't want to image the clouds, because then we don't see the algae. So what could we do to maximize the amount of algae we image while flying over that area? Let's see 3 steps. So first of all, we have 2 cameras. We have the hyperspectral imager, which we use to detect the algae, and we have an RGB camera, which just is a single snapshot of an area. So what we do is we take the satellite, and before we fly over the algae bloom, we look ahead in the orbit and take an RGB image, and then take this image, figure out where the clouds in this image are, and then we compute a path to slew the satellite, so you can move the satellite and kind of picture parts that are not right below the satellite, but maybe to the left or to the right. And then make sure that we kind of avoid the clouds, make sure that we stay within the operational constraints of the satellite, and then we don't slew away too far from the area that is right below the satellite, because if you look very far to the side, you image a lot of atmosphere and it becomes very difficult to classify algae. Okay, and since this is a lot to take in, let's do this a bit more visual. So we start with the look-ahead capture. So this would be a typical RGB image. It's actually one from our HIPSO-2 satellite. Then we find out where the clouds are. Nice. For that, we just look at the RGB values and look at radiance and saturation values for each pixel. No machine learning. I'll also go into detail why we don't use machine learning for this. I mean, this works, but you might ask, because everyone is doing AI these days. Then we do rectification. So as you can see here, we kind of look at it not head-on, but we want to look at this from the top, because the geometry, as you can now see if you compare, the geometry of the clouds changes a bit. So we rectify the image and pretend like we're looking from the top. This is a geometric transformation. And then we also do a distance transformation. That means for each pixel in this rectified image, We check how far away is it from a cloud, so we can then use a very nice pathing algorithm. Looks scary, I'm going to go into that in a bit, to basically figure out how we should point the satellite. And essentially what we just do there is we have a step size, so we start down here. We would imagine that we go kind of along this line to image. So the HSI capture is always a stripe of the ground. And yeah, we begin here. Then we have a step size and we figure out, okay, maybe we want to go here now. So we go ahead a few pixels. Then we take a look. Is there clouds there? Yes, no. If there is no clouds, great, we take this part. If there's clouds, maybe we take a bit of a look to the right, or we take a bit of a look to the left. And we do this for all the possible kind of values along one of those lines. And then we find the one that has the least clouds. That's just a greedy algorithm that we use there. So we just jump at the best, and then we make sure that we stay within the operational constraints of the satellites. We put the coordinates into our path and repeat until we're at the end of the image. Yeah. So this is not so easy. There are some challenges with this. We have a bit of a trade-off situation. If we take captures that are looking very far ahead, so we point the camera almost at the horizon, we of course see a huge area, so we can see a lot of what's going to happen in the front. But the problem is, if you look at the horizon, you're also looking at the cloud side on. And if you look at the cloud side on, it's kind of difficult to figure out what it looks from the top. Also the georeferencing, so figuring out what pixel corresponds to what coordinate on ground becomes very inaccurate if you look far ahead, because each pixel corresponds to a huge area on ground, a few kilometers even with the resolution that we have. However, if we have a low off-Nadir angle, so we almost point the satellite to the ground, then we run into a bit of a time problem. So this graph here on the right demonstrates this. So here we would have an off-Nadir angle of 66 degrees. This is the most we can do with the geometry of our orbit. This is nice. Here, this is a real computation of, I think it was yesterday. And we would do that here, and then we have about 6 minutes to do all of the computation and to turn the satellite back to the ground and take the image. But with 66 degrees, this is way too much. We don't see anything useful. We cannot do the visual computation. So we could say, maybe we try 55 degrees. This is a bit better. It's still not ideal, but also if we do 55 degrees, we have less than 2 minutes of computation time. And considering the fact that we're not sporting a huge computer on the satellite, but kind of a small microprocessor, 2 minutes is tight, it's doable. But then once you say 30 degrees would be really nice, but this is not doable because this is less than a minute, and this is actually also almost the time the satellite will take to turn back, because we can only move at 1 degree per second. So what do we do then? First of all, lightweight algorithms. I already said we don't use machine learning, because machine learning on a tiny ARM processor is interesting. Also, the pathfinding algorithm is probably not the most accurate algorithm ever, or the one that finds definitely the optimal path, but it's fast, so that's why it's used. And the other thing that is also kind of a low-hanging fruit is to just downscale the RGB image. Processing 20,000 pixels takes considerably longer than processing about 3,000 pixels. So that's another thing. Of course, it decreases the accuracy, but after all, we just want to see clouds. It's not something where you want to look at something very tiny. It's a cloud there, they tend to be big, so that's fine. Okay, so in summary, we've seen a nice onboard pipeline for looking at taking an RGB image, look ahead, segmenting it for clouds, and then computing a path that lets the satellites do around clouds, so we can avoid imaging the clouds, especially in our area where we want to capture large areas on ground. This is a very feasible thing to do. Of course, if you want to target a specific city, if there's cloud above it, then you're out of luck. In the future, what I want to do is put this into operation on our Hipster 2 satellite, and then assess
how it actually performs in a real-world situation with our scientific goals in mind. There will also be more closed-loop integration with the potential onboard scheduling on the satellite, so that we can also have different kinds of scenarios where you look ahead in the orbital path, see if there's cloud, you can cancel capture and reinsert it later in the schedule. At the moment everything is done on ground, but it would be nice to have more autonomy and have the satellite decide itself if it takes a picture or not. And also it has to be integrated with the satellite's attitude control system, but sure, of course, it's normal. And then after everything, we have integrated this, there should also be a bit more of a quantitative analysis with the scientists to actually use my data or the data of our lab to see how much we improve using this. Okay. Yeah, so thank you very much for listening. I would recommend you check us out. There are a lot of colleagues of me also here from the Small Sat Lab. They do a lot of awesome stuff, so if you see one of them, feel free to ask and go to our website and use our data. Other questions?
Yeah, I was wondering if it's just RGB value evaluation, how do you distinguish between clouds and snow?
Yeah, that's a good question. So I use something called Klahi. That means I look at 16 by 16 pixel clusters, and snow tends to be much more uniform than clouds. The image I showed is actually not ideal because it's overexposed. If you take lower exposure pictures, clouds have more structure and you can actually see the difference. Also, when you use gradients and saturation values, you can distinguish between clouds and snow, because then you compare two color spaces, and clouds and snow look different in those color spaces. Yes?
I got a question regarding the propulsion system. Maybe you're not an expert in this, but I was wondering how high the expected delta V requirement would be to do these maneuvers.
We don't have propulsion. This is all just attitude control. We use the reaction wheels and point the satellite.
Yes, for Tim. But if you have like this agile path planning, you must be able to follow this new path, right?
Yeah, you turn the satellite. It's going along a line, and you turn the satellite to the sides.
Okay.
That's how it works. Using propulsion for this would be a huge waste of resources. Who was first? I think you in the back.
Can you give me a bit more details on this cloud, how to introduce some stochastic?
More detail on the cloud detection.
Yeah, or just this simple message.
So we have an RGB image. Should I go back to the image or? Okay. There we go. So this is just RGB. So we have 3 values for each pixel, from 0 to 255. I convert this to CMYK, and then I look at the radiance value. So that's a measure of how bright this pixel is. And then I look at the saturation value, and the saturation value is how colorful a picture is, how much the color shines through. And combining these two, I set 2 thresholds, and then just combine, and then I say if it's a cloud, it's probably in the upper percentile of radiance and in the lower percentile of saturation. And it turns out with snow, the saturation is way higher than for clouds. And also then I go through the entire thing in clusters, and if I look at the 16 by 16 pixel grid and do the analysis on the 16 by 16 grid and compare it to the next 16 by 16 grid, I can detect structure of clouds, but snow is uniform, so I would not detect it. Yes?
Yeah, from a more practical perspective, so you're doing these look-aheads, but so you basically look ahead and then you turn the satellite again to the acquisition, or are there 2 different sensors? So you have one that...
Yeah, sadly the RGB camera and the HSI camera, they're next to each other, so we have to turn the satellite back. Of course, let's say we put this satellite into orbit
in the future,
that way, and then someone figured, oh, we should do this. Of course, if you're now designing a satellite, and we're working on the HIPSO 3 mission, And I am pushing for having a sensor that is constantly looking ahead and also maybe to the sides, because there's a lot more you can do with dynamic pointing. You could also detect fires or volcanic eruptions, whatever.
Can you tell more about the hyperspectral camera? Because
I can't really say a lot about it. I'm not the hyperspectral person. I'm more of a satellite person. But I would recommend you talk to a colleague of mine. He knows a lot about the hyperspectral camera systems, and he's doing the calibration for it. He gave a talk yesterday.
So when you see these clouds, they will somehow be kind of trying to make the group of the satellite somehow avoid it, avoid the cloud. How do you do that? How the satellite avoids those clouds?
So there are 4 reaction wheels in the satellite, and when you point the usually the satellite is pointed so that it looks straight down, so it looks down. And then you can use reaction wheels to turn the satellite and just have it point to the side. And then you can follow a path like this one. So usually you would go along this path,
Okay.
but then you just turn the satellite to the side, and then you can do that. And yeah, what this algorithm at the end does, it gives you a sequence of vertices, and those vertices are then pointing quaternions with PCI coordinates, and the satellite just follows this path. Luckily, our ADCS actually supports just giving it a quaternion sequence, so that makes it a lot easier. Okay, I guess no more questions. Then thank you very much.
I guess we're done for the morning. So now coffee break.
trajectory. No. Do we need to speak?
No, if you want, you can connect that. No, they said we should use this and just speak
So
loud.
small.
Yeah. Like for the last session, everyone was not using that.
But
They
in
all
the
were
stream-
using it and they didn't hear it on stream.
Oh, in the streaming they couldn't hear, right? In the streaming. But
Yeah, in the stream
it's so small.
no one was using the mic. Like I offered them,
And,
but
I don't know.
I mean, it's been rare. We have to present it.
When you present this number, can you?
Yeah, I did.
Yeah, just- It's very nice. So many items. Which one is yours?
They haven't, but the right ones were ours for some time. It's in the hangar.
Good morning. Welcome to the rocketry session. Yeah, we will have 4 presentations today. I will start with the first one. And yeah, it's still 1 minute. But yeah, this is a nice picture actually. This is Estonian Aviation Academy in Tartu. It's next to Tartu Airport, so please travel to Tartu and come to see this institute because it's quite nice. Look at the shape and and every lectures get a free airplane. So if you manage to teach there, you get your own airplane and can go wherever you want. Morning. Morning. Do I need to present the agenda first or?
No, we can just start with it.
Okay, it's 45 sharp. Let's start. Welcome. Okay, thanks everybody for being here. Today I'm going to present rocket propulsion education at Estonian Aviation Academy in Tartu, Estonia. About myself, my name is Tiziano Fiore. I'm a guest lecturer at Estonian Aviation Academy in the domain of rocket propulsion. And yeah, my contact for any questions and Estonian Aviation Academy as well. This is this year team. Students are here together with me. And yeah, I'm going to show you what we are doing in Estonia about education, but also the couple of projects we have been doing in the last 2 years related to rocketry. Okay, but first question is why it's so important to be in the education of rocket propulsion. At least it's my personal goal. Is that okay? We are witnesses an increased interest in space. There are satellite constellations happening already. Actually, Starlink is already there. Amazon is already has been launching. It will continue. OneWeb. There's a lot of interest, and this has an impact on life on Earth and beyond. And rockets are essential to enable the space access. Satellites deployment, of course, and then they are also representing strategic systems for the defense scenario. Nowadays, it's getting more and more important. So you can basically translate technology from rocketry to defense as well. And Europe needs new class of engineers which have hands-on capabilities, but also system thinking. They are both generalists, but also they have deep knowledge on a certain technical topic. So my opinion, education must bridge this physics, system level thinking, and real world application why this course started in Estonia. Basically in 2023 I was a bit bored at home. I said, okay, Estonia, nobody's doing anything about space propulsion. I start approaching people around, and then I said, okay, I will design a course. Then I will start getting people around and teach. My background is in aerospace. I graduated in space propulsion in Pisa in 2010 in Italy. So I have a good knowledge on this topic. I also work in several fields, but I did several projects with European Space Agency, so I know a bit about propulsion. So I said, okay, but why not proposing? And then finally, Estonian Aviation Academy accepted my idea to build this course. I built this course, and a short summary of this course was presented in 2024. We had a summer school together with the University of Tartu, Estonian Aviation Academy. We presented this course, and then finally in fall semester 2024 we started officially teaching this course, and now this year we have been now in the second year, and this is just for your info, an ArcJet thruster I developed when I was working in Italy at the University of Pisa. This is the summer school we have been doing 2024. It was about space tech topic. Okay, this is a futuristic view of electric propulsion, plasma thrusters. Okay, this course, my goal is to provide a solid theoretical knowledge. So you see here a bunch of equations. Students nowadays don't like much equations, but everything starts from the theory. I really like to bring up the theory, and the theoretical part of my course is actually coming from California Institute of Technology course, which my professor in Pisa was, taught me, and I brought up in this course as well. So we will, in this course, we cover the basic propulsion systems, but also we focus a lot on the applications. Okay, how these are used today, in which technologies, both on rocket and missiles. Said before, we want to have students to develop hands-on capabilities, but system thinking, also engineering decision making, risk mitigation plans. But the main goal is to learn the physics, build the system, fly the rocket, and you will see what we have been doing in the last 2 years. What are the audience? Nowadays we have students from curricula, aircraft engineering students, but it's an open course. Everybody can register within the Estonian Aviation Academy. Hopefully this course can be opened up to a wide audience, also from other universities they can come. But we also have defense professionals, missile professionals attending this course and coming to me with the need for more theoretical understanding. So anyway, if you are interested, if you are defense professionals and you want to get involved, or at least on academic point of view, or just learning more about propulsion topics, missiles, you can contact me. Of course, we are going through the basics, solid rocket motors, liquid rocket engines, hybrid rocket, and what we also do, advanced orbital propulsion, the chemical thrusters, electric propulsion, all-effect thrusters, ion engines, ion thrusters. But we are also covering some high-speed applications like ramjet and scramjet propulsion systems. The course, as I mentioned a bit before, has a strong basic background. So we cover the thermodynamics, the classic rocket propulsion theory, combustion, all materials used in aerospace. Also the plasma physics, which enables the electric propulsion, ion propulsion. And we also cover the framework, how you design a rocket system, how you qualify it, how you test it, how you deploy it, operational. And we also discuss about test benches, measurement systems. And the last part is about project management in the project management framework used by European Space Agency. In January 2025, the students actually successfully designed, built and launched first Estonian rocket. This is the assembled one, and then the launch was in January 2025. This is a video made on the launch base, and actually you see the rocket here, the students here, and we reached 439 meters. Actually, let's see if it starts. No, it doesn't start. Actually, no, it starts the video. The video is 1 minute, 1 minute and 20 seconds. I wanted to show you. Maybe I'll get out of the. Okay. Let's try to open it. So I think the video is the most interesting part. To enable the change of privacy setting. Okay. Okay. But can we open YouTube? Okay. Let's move on then. And if there are a few minutes, we can check it later. Okay? We can't look at it. We can YouTube.
Oh yeah, we can just share the screen.
But how do you know? Can you get the link from here? Otherwise I need to find it. It's okay also. If you can enable the audio. Okay.
On the laptop is not
Okay, audio is actually not working, but yeah. This was January 2025. First prototype students made. A lot of snow. Test control, we had a specific risk assessment and the launch. Up to 439 meters. And we were recording data in real time with the telemetry system, where we could see the video and parameters like acceleration, velocity, and then the parachute is landing with the avionics on a frozen lake. Okay, good. Thanks. Okay, now Erm from Estonian team, students team, will show you the from the Aviation Academy team will show you the current project ongoing.
Yeah, so hello, my name is Erm. I'm the project manager for this year's course. Well, last year they tried to hit the 500-meter ceiling. This year we wanted to 1 kilometer, so go half the height. We use all the off-the-shelf products. The motor they used last year was the strongest one which you could get without a license, so we wanted to use the same one, but we wanted to have like twice the height. So we had to do a lot of weight reduction, optimizing. We also improved aerodynamics quite a lot, and we sized down the rocket almost like over 2 times. We also put a lot of emphasis on the good documentation, to have documentation good, procedures written down. So usually that's the thing that is lacking. Go to the next one. We study aeronautical engineering. We have like a lot of knowledge about aviation, airplanes and stuff. So this course has been given us a lot of insight to how the rocketry works and how we can make it useful for ourselves. I think that every school should have this course if possible for the schools. If possible, make this course in the engineering field. And if you're a student and you have a possibility to take this course, you should definitely take this course. It gives you a lot of ideas. For example, for us, we know a lot about airplanes, how the airplanes work and everything with that. And now we have an idea how we can make the rockets useful for the aviation sector. For example, maybe some jet-assisted takeoff systems with solid boosters for airplanes. Especially for now, drones. Drones are very emerging at the moment. So jet propulsion takeoffs for model airplanes. You don't have to have a runway, you can launch them very easily and very high and very fast. So yeah, this I can continue.
Yeah, this is the prototype which will be launched next month, right?
Yeah, we have planned to launch in February. So yeah, we're looking forward to it.
Targeting 1 kilometer height. Okay, then just conclusion. Sorry for taking too long. So conclusions is that basically the goal of this course and also the Estonian Aviation Academy mission is to really create an ecosystem and build a new generation of rocket engineers, which can work in not only in the rocket or missile defense ecosystem, but also they can contribute to other fields, because what you can learn in this course can be applied actually. The type of mindset and approach to problem solving can be actually applied to every field of engineering and actually in life as well. Yeah, so in conclusion, just to wrap up, this course bridges theory and practice, delivers real flight experience, and inspires future aerospace leaders. For Estonia, I think it was an educational milestone, at least I hope. It represents a foundation for the Estonian aerospace future, but also it can be a dream from any children who wants to dream about space. Thank you. If there are no questions, or we can maybe talk separately, then I hand over to, because we are 1 minute late. Right?
It's fine.
Yeah, but if there are questions, then let's take.
Do you have any simulators which you use in the course to teach this physics and like the calculations?
You mean for the design?
Yeah.
And for the, yeah, okay. I developed myself one. Basically, it's Excel. There are macro-based Excel, which you can basically simulate the rocket altitude, where it's going, which point reached, and the velocity, these type of things. But then we also did the MATLAB MATLAB model with our control team in the Estonian Aviation Academy. They helped the students to build this MATLAB model, and this is based on control theory equations and coupled with the flight equations. But the students used also a lot rocket sim and these open rocket simulation tools available today. And actually there is quite well match between what you can find, it's rocket sim and what was the other one?
Open rocket.
Open rocket. But I'm a bit old school guy. I was using my Excel and MATLAB model to and one thing, for example, what I noticed when we did this, we reached for a previous rocket 439 meters. My model was a bit different than open rocket, and one thing what I realized that I think that day it was cloudy and moist. It might be that this open rocket didn't take into consideration the weather conditions. In my simulation, I was also putting some drag resistance change with the humidity, moisture, and cloud effect, which this open rocket did not have. So anyway, it's good to trust these new tools, but always build. My recommendation for students: always build your own model with your own kind of equations that you trust, even if they are first order equations. They give you an idea what if you are going in the right direction, and then you can use the open rocket or whatever. Yeah, I don't know if I answered your question, but we did kind of different approaches.
Thank you.
Good. Thank you. Yeah, sure. No.
All right. Thank you. I will skip over the parts you already mentioned.
Thank you.
So I will do it now from a side from the student's perspective of building a hybrid rocket for the European Space, European Rocketry Challenge, EUROC. So why hybrid rockets? As we have heard before, solid rockets, you need licenses pretty quickly when you want to go anything bigger than small motors. And well, because it's explosives. And for liquid rockets, you have liquid oxidizer and liquid fuel. Also that, once you mix it, it can detonate quite frequently, especially if your ignition is a bit wrong. So hybrid rockets combine the two. So you have solid fuel and a liquid oxidizer, and therefore there's not really a risk involved until you press ignition, other than from the substances themselves, which is a lot lower than when they would be mixed already. Also, compared to a liquid rocket, you have just one fuel you have to worry about, one oxidizer, one liquid you have to worry about. So you have half the piping that you would normally need. And compared to solid rockets, you can turn it off whenever you want. Once you light the solid motor, it will just burn the whole time without you being able to do anything about it. So, as I mentioned before, there is this big event in Portugal. It's called EUROC. It's a European rocketry competition, and there is about 50 or 60 applicants every year to try to go there, and then they select about 25 teams. So last year it was 8 solid motors, 9 hybrid, and 11 liquid engines that flew. And for us, the goal was, well, there's different categories you can compete in, and our goal was the smallest, so the 3-kilometer hybrid category. Yeah, that is what you already mentioned. Student rocket projects, they offer a lot of hands-on experience you can get. You can work in whatever field you want. You don't have to be a rocket scientist or aerospace engineer or whatever. If you're electronics and you want to build cool electronics that fly in a rocket, that's also fine. If you study aviation and want to do more aerodynamics, perfect. Or also, whatever engineering you do, it will always help you with problem solving, with how you manage a big project, interact with other people, and so forth. So for the choice of oxidizer, there is basically two non-toxic oxidizers which you could use. One of them is nitrous oxide, and the other one is liquid oxygen. Everything else, well, it might give you cancer, so that's not used. Liquid oxygen is better performing, and is what big rockets also use. The big problem with it is it's cryogenic, and it's oxygen, so it tries to burn everything and react with everything you have there. With nitrous oxide, we're working at about room temperature, but pressure is about 60 to 70 bars. Try to optimize your efficiency there, and it also tries to burn most of your sealant material, so you have to have valves which are still oxygen clean. So what we were aiming for is about a 5-second burn time for the engine. Performance, it's a bit hard to find the combination of ABS and liquid oxygen. So we assumed from EPFL and from NASA simulations what it should be, and we just took the lower end of it because we don't want to optimize a lot so we can get flying faster. The fuel is limited to 900 grams. That is because we want to 3D print the fuel grain, and 3D printers, they use spools of filament which usually come in 1 kilogram size. And some of the material we need to print a liner into the fuel grain so we don't melt the engine casing. Yeah, and the targeted dry mass is about 11 kilograms. Maximum would be 14, which would still work. It's always a bit dependent on the actual performance you get and how well you can get a non-friction coating on the rocket. So our design ideas, which is a bit different from what other teams did, we want a very low pressure oxidizer tank system. So in the oxidizer tank it should be about 12 bars of pressure, so we have to rate it for 25 bars to be compliant with all the rules and guidelines. The chamber will be out of steel with a graphite nozzle insert, which is actually missing in this graphics, as I just noticed. And the ABS fuel grain that will be printed to also have a liner built in, so we can get away with a very thin ablative material, so we don't have to replace it after every burn, but maybe can get like 5 burns out of each liner. Why 3D print the fuel grain? ABS has quite a low regression rate, so you need a lot of surface area for it to burn fast enough so you get enough fuel into your burn. 3D printing gives you that ability. So we can do complex shapes like this which you couldn't cast. But for printing that is perfectly fine. And it helps you to adjust the oxidizer to fuel ratio after a test. When you work with a standard paraffin grain and you realize, oh yeah, my oxidizer to fuel ratio is way too low, I need to burn less fuel. You need to come up with new additives, sometimes new manufacturing, because the additives make it brittle, and you can't really change it. With this, you do a new 2D sketch in some CAD software, and you just print a new fuel grain. If it's too high, well, you add more surface area. If it's too low, you remove a bit of surface area until you have exactly what you want. For the pressure system, it is the 12 bars is designed to be able to use scuba diving components because they're lightweight, they're off the shelf, and they're quite low cost. And most importantly, as we can see here, with the green cap, they come in oxygen clean versions because there's technical scuba diving where you use pure oxygen, so pretty much the same problem that we have here. I put in the small diagram, so we have the high pressure tank at the top that will be nitrogen, just at 200 or 300 bars. Then we have the regulator, which is this part. Right, where's the laser? So this is the regulator. Then we have a pressure relief valve. You can also get that from scuba diving. It's about 30 bucks. It's cheap. It's oxygen clean. A bit of pipe here to make sure all these components don't freeze. This is the liquid oxygen tank with its burst disc. And then we have here a ball valve, which has to be an oxygen, well, liquid oxygen rated ball valve, but luckily Swisher is making those. You can just buy them. And then you put a servo on top of it, which is opening and closing the valve as you need. And then we have the engine. For this whole thing, we also need to build a test stand. The most common way to build a test stand is to use shipping container, usually an older, bit bit broken shipping container, because they give you explosion coverage. So when your engine would detonate inside that, you won't injure any buildings, anything around your whole test. So you just need to have one dimension, the one the engine is pointing at, where you need some clearance to other objects. From what I have learned in my previous projects, especially in Kiruna and in Austria, the electronics, you always want to add more stuff. And if you don't have them built in a way that they are able to accomplish that, you end up stitching in new parts everywhere, and it becomes super complicated and no one ever can fix it. So we went away with using robot operating system and micro-ROS, because once you have it running, you can just add a new sensor. It has to have a new name, and you can integrate it within 5 minutes. Just put in the new controller, have it publish on its topic, read it in, and you have the new sensor added. With other systems, you have to have pins ready, and then maybe you don't have a port anymore for that sensor, or your voltage level is wrong, or whatever. It becomes super complicated. And also the test stand needs to be able to perform tank burst tests up to about 30 bars. Because, well, you should try your tank if you build it. It's designed for 25 bars. It's better to test the tank once or twice to see when it actually will burst, so you can be sure it can withstand the 25 bars you have to rate it for, and then you can go with the 12 bars operating pressure. And there will be a burst disc which will burst at a maximum of 15 bars. So it's far away from what the tank can handle. Probably the most important part for all student projects is sponsoring. This is from, the sponsors are from my old team in Vienna. There's a lot of companies who support you financially, or sometimes also just with parts. So for example, we have, where is it? Somewhere on here there's Peak Performance, or Peak Composites, there. They gave us carbon fiber, and I don't want to know how much that costs. There was pre-tracked rolls where they were like, oh yeah, that's about 15K. But it's run off by a month, so we can't sell it anymore. Here you go, have it. Do whatever you want with it. And I mean, that stuff is still perfectly fine, but they can't sell it anymore. And for us, it's the best material you can get. Yeah. So thank you for, oh, now it works. Thank you. Any questions?
How do you use ignition?
Well, with solid motors. So you use a small, like B size or D size off-the-shelf solid motor, take out the fuel drain, and ignite that with an electric match. They burn for half a second to a second, super hot, and they melt enough plastic and ignite the oxidizer.
So did I get it right that the motor is just plastic plus oxygen?
Exactly. So the black part here is plastic. The orange part is a liner. So it's some phenolic paper, which is just there to protect the casing, so the casing doesn't melt. And then here at the top you have the injector plate, and here would be the whole rest of the system, as we can see below. So there's a valve, and this is the oxidizer tank. And yeah, so you have oxidizer flowing into it, and here at the top there will be the solid motors, and they will ignite the whole fuel grain and engine. Anything? Anyone else? All right. Thank you.
Thanks, Thomas. So now we have Estonian Rocket Student Association. Hannes is presenting his project.
So, hello everyone. I'm the project lead of Estonian Student Rocket, and I will give you an overview of our current state of development and plans for 2026. So first of all, about the organization. Basically the idea to create this organization was born exactly a year ago during the Winter Satellite workshop. I just got to know about the Euro competition. I also wanted to see the rocket propulsion course poster. Unfortunately, this one wasn't here to present it, but either way, it was inspiring. And I have liked rockets for many years. The idea to create this organization was actually born even before I got to university. And so that's just last year, the culmination of these events led to the creation of Estonian Student Rocket. So the organization is less than a year old. And obviously the goal of this organization is to bring new competences into the Estonian student projects. No one in Estonia is doing that in that scale that we are doing and what we are aiming to do. So a lot of companies, be that in defense or aerospace in general, really need people with these skills. And since we don't have any big technical universities with aerospace degrees, then we can fill that void. And so one way that you can really inspire people and give hope for the future is through promoting that, and we can do that really well with, for example, the Euro competition that I'm going to talk later as well. Here you can see our current team. When we first started, we basically had 5 active members. Now we have 10. So the first prototype was done on an extremely tight schedule and with quite a small team. These are our 2 big mentors, one of them being the Estonian Student Satellite. As I'm also part of Estonian Student Satellite Foundation, then the people who have been part of this foundation are really skilled in electronics, programming, project management, and there's a lot to learn from them. Also Tartu Observatory, who very generously give us access to their labs where we can, for example, solder our boards, have meetings, hang out. And so the current state. As many of you have probably seen our first prototype, then the goal for this is to just learn as much as possible. It's not meant to be the most efficient or the best or anything such, but just to teach us enough about rocketry so we can go forward with more complex models. So yeah, currently the goals for this is to reach about 700 meters. And as I mentioned, the first test actually or the launch attempt took place 2.5 months after the development started. So we were on the launch pad 2.5 months later after we started. And unfortunately we didn't launch because the igniter wasn't installed correctly. And so it didn't ignite the APCP crane, and but everything else was in place, and if it was installed correctly, we would have flown. But we have learned from our mistakes, and phase 1.1 is ready to fly. Hopefully the test flight will take place next Monday. So about mechanics, currently it's quite simple for phase 1.1. We're doing as much as possible out of basically PTG because it's quite simple to just design something and print it out without having to create complex manufacturing processes and then just reinforcing it, for example, glass fiber, and learning about different processes with that. Also, we want to create our own avionics. The first goal was to just get the whole to get all the sensors working so we can get the data, and I'm going to talk later what we're going to do with that data. But yeah, first of all, just proof of concept that we can get the data out of sensors and then do something useful with it. Also can't forget about ground support. It's quite easy to actually. So here on the left you can see our launchpad, and on the right the launchpad controller, which is then responsible for igniting the motor igniter. And so with the first test we wouldn't have needed that like big launchpad or that sophisticated communication system, but as we were developing phase 1, we always kept in mind that we actually want to scale up and go bigger. So from the get-go, we didn't want to cut any corners in that sense, but we did, but we learned from the mistakes. And so what's next for Estonian student rocket? The goal for Estonian student rocket is to reach or to get to EUROC 2026. So we visited EUROC 2025 last year. It was incredible. The atmosphere was one of a kind. I can't really put it into words how really amazing it was to be there. There's a lot of like-minded people together, building very complicated technologies. And so if you actually go there, and even if you don't have a rocket like we did last year, then they're really friendly and want to help you out. And so as Aldo's presentation already mentioned, then you have two altitude categories, the 3 kilometer and 9 kilometer. We want to compete in the 3 kilometer category and using COTS solid, which is the easiest for teams that are just starting out. But yeah, as you can see, there's a lot of happiness once the flight is over, and there was a record number of ballistic flights this year, which was a good reminder that parachutes are important. Recovery can't be just an afterthought. So there was a lot to learn from this year's EUROC. Yeah. So as we're just starting out, but a lot of the teams that have been doing that for 10 plus years are developing their own liquid motors, hybrid motors, and so the complexity with that grows exponentially. So yeah, one day we'll get there. So timeline for this year is as follows. Currently we're in the phase 2 development phase, where we have already started with requirements. We have already made some test articles, but yeah, phase 1 really taught us a lot of lessons that we can now put into use. Also different contacts from EUROC who have given their technical reports are really also helping us out to get to EUROC in October. And so what are we currently doing? On the right you can see our first airframe test tube. So for this EUROC rocket, we can't be using like this quantum tube or this polymer mixture, but we will be building our own glass fiber airframes. And so this was just to learn about the process, and yet again you learn the best by doing things. And as a side mission, we also want to have CANsets as a payload, and for phase 2 we plan to eject them, 6 of them, at 1 kilometer. Electronics wise also, EUROC was quite a good resource, visually good, interesting, different like approaches, and the main thing, or the takeaway was that we want to have this backboard where we can just stack these different boards, electrical power system, communication, onboard computer, and in the future, if we plan to use, for example, CAN, we can make it really modular, so you don't have to have assigned slots, but just put any of the boards wherever you like, and you have a really modular system that doesn't have to be just about the current prototype or the Euro competition, but can be used in any similar type of rocket. And so the current software architecture. So as I mentioned, the idea why we want to get all the sensors working are because that one of the goals for the Aero competition is to reach this altitude very accurately, so either 3 or 9 kilometers. And the way you do it, or the most common approach, is that you use air brakes. So what it means is that you have, for example, a bigger motor than you actually need. You would actually overshoot. But since you have air brakes, you can bring your speed down and brake to the set altitude. And so if you have IMU data, parameter, and for example magnetometer, then using that data, feeding that into state estimation, currently we're aiming to use unscented Kalman filter, then you should get a really good prediction of where you should start braking. And yeah. Simulations-wise, we haven't done anything really sophisticated yet. The main two programs are RocketPy and OpenRocket. OpenRocket is just a really good way to see your stability, and yeah, just to be sure that what you're gonna send up isn't gonna cause any harm. In the future, as we also want to use air brakes, we need to CFD, so just know that at what airspeed, how much the air brakes are gonna slow you down. And also, as I mentioned before, that we haven't optimized anything yet for the first prototype, but for example, the next prototypes, we want to actually be sure that the fin shape, nose cone, anything related to that would be highly optimized. Here you can see one of the plots for the upcoming flight. One good thing about RocketPy is actually that it also takes into consideration the flight model. So basically, I think it was 24 hours before the flight. You can generate this simulation, and it will have a really good model of what the weather is, the temperature, humidity, other things like that. And from the support, of course, the Tartu Observatory, who have been very generous, and also the Euro visitation was really useful in terms that we got in contact with many great teams, and yeah, they have been nothing but friendly, and yeah, sending us their technical reports where we can learn from. And our 4 official partners who support us financially are Frankenburg, Treod, Ecom and Eisler. For example, Ecom is able to manufacture different powder printed parts, aluminum parts, and Eisler is producing quality PCBs. But with that, I'm done. If you have any questions, I'm happy to answer them.
Questions?
Come on, we can do better.
I'm just wondering, where do you get the CAN sets, or how do those fit into your plan?
Yeah, so CAN sets are done, or the organizers are from Mesero, and so this competition has taken place now a couple of times. And so high school students, middle school students are building these small satellites, that just have their own like mission. If you eject them at 1 kilometer, then they have their own small parachute. They will slowly come down and beam telemetry to the ground station. And so bidding them is just that since they have this form factor, then we actually had to design phase 2 around them. So phase 2 will be around 3 meters and 90 millimeters wide. So to fit all the 6 gansets there. Yes.
Any plans for a two-stage rocket?
What a great question. Not currently, as like the second stage ignition could go wrong in more than one way, and just to say the least, isn't trivial. Like it would be a crude engineering challenge, but there's no point in that scale to do it. Maybe if you want to do a space shot, for example, then it would be really, really useful that you have two stage. You have the boost and the booster and the second stage. But currently no plans. We're just really focusing on meeting the timeline and to get to Europe in October. But if no other questions, then I'm done. Thank you.
Now there is another presentation, but we have Reina, sorry. Here. Okay, so Reina is not here, so I believe. So we were supposed to be another presentation, but we don't find the presentation uploaded, and the person is not here to present. So anyway, thanks.
Maybe I can use the moment. Alto Space Association will launch a few rockets tomorrow, right behind here on the ice at 5:30 in the afternoon. You're all invited to join. Watch some small solid rockets to fly to about 100 meters.
Interesting.
That was all.
Yeah, thanks. No. Yeah, but then session is over. If there are more questions, then use the time. Otherwise, thanks. Thanks for coming.
Yes, so welcome back from the lunch. I'm Esa Kallio from Aalto University, and I'm sharing this session. And I think that we are already now 2 minutes late, so it's a pleasure me to introduce our first speaker, Topi Räty, and the name of the presentation is For Sale 1P Early Mission Status Update. Please.
Thank you, Esa. So I will be presenting For Sale 1 Primes, the satellite launched by Aalto University, and For Sale Consortium Early Mission Status. So For Sale 1 Prime is launched by the For Sale Consortium. The project has been ending now, but we are excited to get the data down in the coming years. And here you can see the contributing institutes. The satellite carries 2 main payloads, PATE particle telescope built by the University of Turku. It will measure energetic particles in the low Earth orbit. And we carry as a secondary or the other primary payload, plasma brake built by Finnish Meteorological Institute. And this is a technology demonstration trying to demonstrate propellant-less way to alter a satellite's orbit. In the low Earth orbit case, deorbit it without propellant. Then we also have in-house built secondary payloads, a Raspberry Pi-based camera, as well as a MATI magnetometer. And I will return to the camera quite shortly. We also built all the avionics, the structure, and solar panels in-house. And on the top there, you can see the avionics block. It's not much bigger than a fist. And on the bottom there, you can see the flight model flat-sat testing stage, where all the flight hardware was on the table, integrated in an easily debuggable way for early testing. We also have our own command protocol and ground station, which are not big focus here. For Sale 1 Prime was launched last year on the Transporter 15 on board deorbit's ION spacecraft. So we had an intermediary phase after launch, where after a week from the launch, we were deployed from a CubeSat deployer you see here. And in December, when we were deployed right over Siberia in the early morning, and over Finland, we saw the deployment sequence do its job, and we caught the first beacons from the satellite ever. Our pointing was, however, a bit misaligned, so the signal is quite faint on the spectrum, but we managed to manually calibrate the antenna towards the satellite and get a bigger signal at the end of the overpass as well. But quite exciting that we saw the first beacons even from a side lobe of the ground station. For the next overpass, we had calibrated the antenna correctly and our tracking was on. So at the start of the overpass, we already decoded the first beacon. We established communication on this overpass, updated the clock on board, as well as checked telemetry on the deployment, and we could see that everything had run smoothly, and on the first attempt, the satellite had, in fact, deployed. Then about how cameras can talk. So the first day, we were excited that we had really good connection. We have also configured the camera to take images during deployment. So once it exits the pod, it takes a sequence of images to confirm a clean separation, and also just for fun. And we were excited to see are the photos there and what they look like. So in the afternoons or evenings first overpasses, after we had checked more system health, we powered on the camera, and then the overpass seemed to end as we lost communication. Well, then the next overpass came. It was supposed to be a higher elevation one, so we could see it better, hear it better, and we did hear it, but no commands were going through. But maybe it was interference from Europe, maybe Ukraine section, so just a fluke. Let's see the next overpass. Next overpass comes around, and we see that still the satellite is beeping constantly, the health is okay, but it's not getting our commands. So we're not seeing any response to what we're sending. And this continued for a couple of days before we could figure out what was going on. This figure tells you the real story behind why we lost commanding signal. So the orange line is the signal received by the satellite from telemetry recorded there and transmitted down automatically. And the blue line is the background noise it hears. And on the first day, the blue line is quite low here, at roughly 0 dB, sometimes going up to a couple dB. But after the evening overpass, it jumps up to 10 and stays there for an extended period of time. And after that, not a lot of commands go through, and eventually we get nothing through. So could it be the camera then? And how can it be the camera? We check on the flight model spare, which we also have, has the secondary payloads as well. So we powered on the camera, and there we get a much better time series of the housekeeping because we can receive everything. And there, again, as we enable the camera, the background noise raises almost 10 dB immediately and stays there flat. Well, then we go to investigate online. Has anyone had any EMI experience with the Raspberry Pi Zero, which we used in the camera? And a lot of people are reporting EMI there. So quite unfortunate that we put a radio jammer on our satellite, but didn't think to include in the sensitivity tests camera next to the radio system. No worries though, since we have automatic fault detection. The system was otherwise quite stable, so it iterated very slow. We got a nice 3-week holiday from the start of December after figuring this one out. And on the second day, almost as if planned, the system did a full reboot, turning off the camera, and immediately contact was restored. And we could command it from the very first low orbits going over northern hemisphere and Greenland. Then we proceeded to check the payloads, which we had not done on the first day's overpasses. Payloads were reporting fine, and we managed to even do some measurements later. PATE is here, the particle telescope, reporting a ton of data, which you might get more from Turku's presentations. And here the plasma break. For us, these lock statuses are important, so all locks survive the launch vibrations. After running some first PATE missions, we did a full orbit scan, you can see there on the top right. And we were just scanning without much attitude determination and got energetic particles detected already on the first runs, which was exciting. And this can tell that all the detectors on PATE are working as intended. Unfortunately, since we had the delay, we don't have much more data on PATE at this point, but currently there is a big sunstorm going on, and we are recording that data as well. We also started downlinking the images, so we can still use the camera. We just have to sequence the operations such that they don't happen during overpasses and the camera is turned off. So we managed to transfer the deployment image sequence as thumbnails to the onboard computer and downlink it. And here you see all the beauty from the deployment. Seems like it happened on the night side, but we are also downlinking the first image to maybe find out some detail in there. Maybe we can see stars as well. Then we went on to the ADCS commissioning, see sensor health and data, and the sun vector was working nicely. Some calibration on one sensor is required. Gyros are also staying pretty constant, but you can see some gyration there. and the tumble rate is also staying very low, likely due to our pretty heavy satellite, especially on the outsides. Here you can see some of the raw data from the sun sensors, which are then combined later into the holistic sun vector. And then you can see some discontinuities in the z-coordinate as one sun sensor's calibrations are a slight bit off. So retuning is needed there. Here's some data from the digital sun sensor, which we have only on one side. So that's why you see mostly noise. But as we enter the sun on another side, the digital sun sensor is also drawing very nice constant graphs. Then we also have 4 attitude determination control magnetometers on board. We did a degaussing and calibration ahead of launch as well. And those calibration values on board seem to be a bit off, or some magnetization has been happening. So orbital calibration is in order, but the sensors seem health-wise fine. And here's the gyroscope calibration data, again, a bit more elevated. Next steps for the satellite will be record more pattern data, run longer calibrations, fix some errors in the ADCS algorithms, patch the software on the satellite so that we can, or update those ADCS algorithms. Then a big priority is to demonstrate the plasma break. We will do a small reload test once we have rotation achieved for the ADCS, with the ADCS, get more images from orbit, test this radio amateur repeater we have on board the UHF, as well as automate the overpasses in the future. Thank you. This was quite technical, but that has been our last weeks. Hopefully you got something out of it. And if there are any questions, don't be afraid to shoot them. You can also see live overpasses there at other universities' booth along the last few days of the conference. Thank you. There's one.
Very interesting questions and presentation and congratulations. So questions, please.
Okay, thank you for your presentation. Just one question. How are you allowed to keep your payload on during deployment? Because normally launchers require that all payloads are cut off with kill switch for at least 30 seconds after deployment.
So we were only required not to transmit right after deployment, and the camera sequence isn't that fast, fortunately. So that's how we cleared it.
Yes. More questions, comments? Yes.
Could you comment on the magnetic field plot you had on one of the slides? What's going on there?
I can a little bit. There was a weird discrepancy which we haven't been able to investigate yet. But yes, this one. So it could be that the calibrations we have a slight bit off. Over the poles we're reporting something weird, but it should be more continuous. So it's likely that maybe some other system on the satellite has been generating this. But this is to be investigated. This is very early data, just downlinked last week.
Yes, thank you. Unfortunately, we have to stop and now move on. So let's thank the speaker once again. Yes, good afternoon. Yes, my name is Esa Kallio, and I'm going to present our Suomi satellite, actually something what has been happened during the 7 years, not everything. But I will focus to tell about our recent observations and our data analysis and the associated so-called ice cut heater experiment, and I will come ice cut and especially now HARP heater experiment. I will come back to that a little bit later. Yes, so first why we are doing this kind of research, then briefly about the Suomi 100 satellite and especially its radio spectrometer. Then the focus is on heater campaigns. I just remind briefly about our previous ice cut heater campaigns, but main focus is HARP campaigns and something new what we would like to do. So the motivation is, or one motivation of our satellite is that we make ionosphere research, and in this image it a little bit illustrates so-called active measurements that I'm now talking about. We have a here transmitter, and we can control what is the frequency and how we use it, and then we are flying above this heater and we are listening to signal. Can we hear it? And if we can it, how strong it is, how it is modified. And in such a way we use those radio waves for ionosphere diagnostic purposes. So the goal is that investigating those signals, we understand better the natural behavior of the ionosphere and also how the heater is actively changing the properties of the ionosphere. Wrong direction. Then about the satellite. The satellite is a very small 10 centimeter, 10 centimeter, 10 centimeter in size, about 1 kilogram. We have been in space about 7 years. It's a sun-synchronous solar orbit at altitude about 500 kilometers at the moment. We have 2 payloads, but I will not now tell about our camera. I focus on our radio spectrometer that we are using on ionosphere research. Yeah, actually here you can see 2 ferrite rod antennas. And actually I will come back to those antennas and their features when I will look a little bit later. So the name of the instrument is here. Here you can see the frequency range, and it is in-house made at Aalto University together with the Finnish Meteorological Institute. So this reminds that actually we started this kind of heater experiment with the ice cut heater already 6 years ago. And as you might know, the ice cut heater is here in Tromsø, and there are 2 antenna fields. And in this, our observations or campaign, we used a larger antenna one field, and in the frequency range that we can measure. And actually we confirmed that we can really see the signal, and I will show this example. So here you can see the track, ground track of our satellite. Tromsø is over here. Of course we wanted to fly as close to ice cut heater as possible, and the ice cut was used in 1 second sweeps when the power was from 0 to maximum. And we wanted to make this kind of pattern so that we can really make sure that if we observe something, that is really from ice cut. And also in that, we also could investigate nonlinear response of the ionosphere to the heating power. And if you are interested, you can read more about our data analysis and the results from the paper. But this is the focus. HARP. What is HARP? HARP is High Frequency Active Aurora Research Program. And actually it's the most high power, high frequency transmitter in the Earth. It is in Alaska, near Gagona, and here you can see those kind of antenna field. We made 3 joint observations when HARP transmitted 8.1 megahertz signal, and then we observed 2 times we moved from north to south and 1 from south to north. This red dot is a location of the hub, and this is our closest distance from the hub. This is, I will introduce data that is collected almost exactly 1 year ago. In order to understand the feature of the data, we have to understand the antenna pattern. So actually there are 2. One is so-called pencil beam, and actually the name implies there is a very strong global maximum, and there are then local maximums. But the highest transmission is along the symmetry axis. But this is the beam pattern that will be used in the example that I will show. Twist beam, and actually here, as you can see, at the symmetry axis, the power is not at maximum. There is a local minimum here. The maximum is around the symmetry axis. It's like this kind of ring or cone around the symmetry axis. Okay, so let's now look at the data. Here it's how it looks like. Actually, the count means strength of the electric field. The electric field is changing its direction, and there is a noise. You are not surprised. But then we can see something. It looks to be a signal. Yes, and max high. Then for some reason minimum, for some reason maximum, and back to the noise. How we can understand that one? We can do it when we look to antenna pattern. So here you can see the amplification in polar coordinate. This is the orbit of Suomi 100 satellite, and actually the hub they pointed the maximum transmission to the orbit of our satellite. So and actually if we focus now here, you can see better how this twist beam actually looks like. As you remember, the maximum is around the center. And it looks to be that yes, we moved to the high electric field region, then a smaller electric field, and then back to the higher electric field. So that's the reason why we call this like an in. We are going into the center, then minimum, and then we are going out from the center. And if we now calculate what is the actual electric field along this orbit, we can see that this feature 2 maximum is something what we expect based on this antenna pattern, in and out. So that's of course nice, but let's look a little bit smoothed data first, because there is a fluctuation, and then some details, very less than a 1 second variation. So first about the basic trend. So here you can see the moving median, 500 points, so the window is 0.5 second. This is inside this cone and outside of this cone. And if you compare how the data is behaving and how, according to antenna pattern, what the electric field should be, you can see that yes, there looks to be similar kind of trends both in and out. And if we want to a little bit smooth more, let's take 2,000 point moving median. We can see that yes, it looks to be that this antenna pattern model can explain many things what we can see in the data. And of course, this is so nice, but you can also, of course, see that there are this kind of small time scale variation. And let's now look in more detail this kind of small time scale variation. So we don't know what is the spinning or tumbling period of the satellite, but it might be several times per second. And here we'll make a hypothesis that, okay, let's assume that it's a 3 times per second. And this is a very small data set, 0.2 second, 0.2 second approximately. And you can see electric field is moving up and down, but there are this kind of trend. And as you remember, we have a ferrite rod antennas. And when the satellite is moving, also this ferrite rod antenna is moving. And the physics of this YBC electric field is that the magnetic flux through these antennas is changing. And therefore, let's put this time into the map by assuming that we have a rotation, 3 spacecraft rotation per second. So therefore, here you have, you can see the P angle, and if we put it into polar coordinates, you can see that there is this kind of butterfly. There is, in this region, we have a high count rate, low count rate, and on the opposite side also high count rate. And this is actually Cine function with respect to angle. So it looks to be that we have this kind of pattern, and our work hypothesis is that it is because the spacecraft is rotating. So the highest value we can see when we are looking along the direction where the magnetic field has the strongest changed. I forgot to mention it's a linearly polarized wave that is transmitted. So this is probably the direction of the ferrite antenna when we get the maximum, and you can imagine that after 90 degrees, the ferrite rod antenna is here, it's smaller, and after 180, it's once again larger. And this is actually interesting because this is the second time when we are using the spinning property to get more data than originally planned. Because as you remember, we have a camera. In a camera, because spacecraft was spinning, we could take a photograph from many directions and see better auroras. But now we can actually see the properties of the magnetic field in 2D, thanks to this spinning spacecraft. And then hopefully I have some time, I don't know much. Then we also have developed, of course, numerical tools to interpret those data. And we have 2 type of model approaches. One is so-called ray tracing simulation. If you are interested, please take a look of this paper. So here we have ionosphere, we have electron density enhancement. You can see how the radio waves transmitted from the ground, how they are deviating when they meet this plasma cloud. This is another, now the same simulation, but using this kind of full Maxwellian simulation that we really use brute force and calculate, solve those Maxwell equations. We also see the same features, but now there is also interference effects, all those amplitude effects that are not here. Thank you. Concluding remarks. Yes, so I introduced one example of our 3-hub joint observations when we observed the signal. As you recognized, we can see this kind of basic features quite well understand, and we have also interesting smaller time scale associated to the spacecraft rotation. Hopefully we can accomplish the paper soon. But of course, we could think what to do next. It would be nice to have not only one spacecraft, but maybe second or maybe more spacecraft. And if we are lucky, we can have a possibility to do it, because it might be that we can still be in space several years. The spacecraft is working well, and our instrument is working well. So I'm looking, and the whole team is looking for the new observations. So thank you for your attention. Questions, please.
Thank you, Jari Hänen from Traficom. Have you already tested some heating experiments? How that affects the ionosphere and what you can see with the satellite? Thank you.
Yeah, thank you. So we have analyzed this kind of heater data, and as I maybe here showed, so we have developed a tool to really understand that how this heating, because this heating changed the density and temperature of electrons. And now our goal really is that when we have seen the data, all of those simulations doesn't match exactly to the observations, and that's good, because into those antenna simulations, they doesn't include this kind of scintillation effects. But now we can make simulations and include artificially, manually, this kind of scintillation effects and change the electron density and try to find the best match between the observation and simulations. And actually this was the main goal, to make this kind of heater experiment. Yeah, thank you for the question. Unfortunately, I believe that we have to move on. Thank you for the speakers once again. Okay, yes. Let's move on. And the title of the next presentation is First Propulsion Test Results from the Wisdom Mission, and the presentation will be given by Perttu Yliopas.
Thank you. All right, good to see so many people here. So yes, sharing some first results from the Wisdom Mission that was launched this November. I'll start from going through what the mission itself is, and then in the end look at what we've done this far and what will be the next steps. So very briefly about our company, Aurora Propulsion Technologies. We are a local propulsion system manufacturer making both water resistor jet thrusters as well as plasma brake systems for deorbiting for satellites in the CubeSat to smallsat scales. And as a partner in this mission, we have C3S from Hungary. They are a company manufacturing CubeSat systems and flying multiple kinds of experiments. They have flight-proven platform that they are using on quite a few different, both ESA and commercial missions. Jumping into the actual mission, it's quite an interesting mission. I'm not sure the mic is kind of cutting out. Maybe not. Okay, maybe that's better. What we are doing on this mission is that we are launching a 6-unit CubeSat, which will then in orbit split into 2 3-unit CubeSats. So the point is to improve the space traffic management aspects, especially looking at the CubeSat use cases where CubeSat's capabilities are often a little bit more limited. So how can we improve the STM aspects? The project is supported by the ESA NAVISP program and developed and launched under that. And yeah, as a very kind of brief summary of the mission, we have a 500 512, 520 kilometer SSO orbit, where we have the 6-unit split into 3 units after the commissioning. Then we have the inter-satellite link communication tested, so we have a direct radio link between these 2 3-unit platforms. They are communicating between each other about simulated collision avoidance maneuvers. So essentially, we simulate a collision or conjunction event between these 2 satellites, and then they are communicating between each other that, okay, we have a conjunction, can we avoid this collision? Do you have propulsion? Do you have propulsion? One of the 3 U satellites has propulsion, the other one doesn't. And then, yeah, the collision avoidance maneuvers are basically done in a way that drives the satellites then apart. So of course we need to minimize any collision risk. So after deployment they will be on a very similar orbit, but then once we actually do the demonstration, they will be driven to slightly different orbits. And of course one of the demonstration focuses is the separation mechanism. So how can you actually make a separable satellite that is going to withstand the launch vibrations, but then can on command be split into two in orbit. And the last payload there is the plasma brake. So because on one of the satellites we have the thrusters, the other satellite has the plasma brake in the same space, so we are demonstrating also sustainable deorbiting with the one that does not have thrusters. And we basically integrated this plasma brake form factor into the 3-unit form factor. The product itself is the Tunacan form factor plasma brake, but we adapted it to fit inside the volume. Here's the beautiful picture of the platform right before flight. So you can see the alignment features. Did we have the, yeah. So the alignment feature between the two 3U satellites, and then you can just about see a little bit of the actual deployment mechanisms. There's no public close-ups of that, but essentially it's a hold down and release mechanism, but just much beefier than you would normally see in a CubeSat scale, because it actually has to hold on the whole satellite mass. And yeah, other than the hold down release mechanism, both of the platforms has the C3S OWL, the orbital whereabout locator, which allows them to communicate up to 4,000 kilometers away. So actually the range of that is essentially high enough that they will be limited by visibility rather than the radio. And then there's the intelligent payload controller that handles the autonomous maneuvering and decision making. And as I said, one of them has the 4 thrusters and the other has the plasma brake as subsystems on the remaining kind of payload space. And for those that already know everything about plasma brake, I have a comic for you. But for those that have not heard anything about the plasma brake, it is a Finnish invention, a deorbiting mechanism for any small sat from CubeSat scale to small sat scale, using a micro tether that is deployed from the satellite and generating a Coulomb Jack effect that deorbits the satellite. Yeah, most of you will be very familiar with this, as I'm not going more into detail with that. But if you are interested to hear more, please come to talk to me or to our booth upstairs. So then, finally, the main topic of the talk, which is the first results. So at the moment, commissioning is still ongoing. We launched in end of November after a couple of delays. US government shutdown and stuff like that were pushing it a bit forward. But we have been able to do the ARM-C collision, the collision avoidance system thruster commissioning, which basically consisted of taking the readings from the system and heating up each of the 4 thrusters. And now here you can see the beautiful curves for heating up the thrusters. There's a little bit of a lag in the thermal measurements, and there was not quite long enough duration to actually measure them. So we kind of are missing most of the 4th one warming up, but it's very good to see that all of the thrusters are heating up with basically identical curves, and everything is looking good. All of the thrusters respond and are ready for operations. Currently there is the ADCS commissioning ongoing, and once that's completed, we will then run the first burns on the thrusters. Essentially, we'll be verifying the burn by measuring the change in the spin rate, and this is done before the 6U is split into 2 3Us, so that our center of mass is still on the side, so the thrusters will impart a measurable rotation on the satellite. So we prove that the thrusters are working on that stage, then we deploy the satellite into 2, and then we go on with the main mission. This is expected to happen within a few weeks. Of course, C3S team is busy doing the commissioning at the moment, so let's see when it actually progresses to that level, along with the plasma break commissioning, which is basically looking at the housekeeping values and ensuring that everything is ready. And in terms of next steps, what is coming up is that after the deployment and the collisional avoidance maneuvers, the total mission time is only 6 months, which is absolutely perfect for us because we want to deorbit as soon as possible because we have the deorbiting system that we want to demonstrate. So we are getting to actually deploy the plasma brake system already this summer. So we are expecting that we'll get actual force measurements from the plasma brake later this year. So very excited to wait for those results, and hopefully at least latest next year in the Winter Satellite Workshop I will have lots of good data to share with you guys. All right, thank you. Where did my last slide go? There's a black slide in between, but thank you for listening. Any questions?
Thank you. Could you share some details how the communication between the satellites work, the OWL system?
I don't actually have the more details about that. I only know the very basics because, of course, it's a subsystem developed by C3S. But essentially, it's going to be proven like this is a in-orbit demonstration mission for that link. It's a direct radio link between the satellites, and that has a variety of use cases, which we'll hopefully get to do in the future. But yeah, I don't know the technical details about the radio itself.
Thank you for a very interesting presentation. The split of the satellite, or the separation into two satellites, is that a product that Aurora Propulsion Technologies is developing, or is it just for use in this demonstrator?
So that specific subsystem is also done by C3S. We are, of course, developing very similar systems, so it's very interesting demonstration for us as well, because looking at the larger plasma brake, we have essentially a 5 kilogram system that is attached to the side of a small sat up to 500 kilograms, and we need to deploy that with the tether between the remote unit and the satellite. So we are developing very much similar HDRMs, but the specific design was from C3S.
Could you elaborate a bit on how the propulsion system works?
Yeah, so the thrusters, if we look at the water resistor jet, so the RMC system, this we have them also at our booth if you want to see them in person, but it's a 100-gram module which has a single thruster producing around 1 milliNewton average thrust. We have 4 of these. It's a water resistor jet, so it literally just vaporizes water which jets out of a nozzle producing the thrust. On this one, since the module is series produced, it's actually much cheaper to put 4 of them rather than develop a custom bigger thruster. So we just sold a bunch of 4 thrusters which were all installed. This of course provides the customer with redundancy, because if any 1 or even 2 of those thrusters fail, then you would still be able to operate, and basically you can also get much higher thrust level. So there's actually a lot of benefits of using multiple small thrusters rather than making like a custom-made bigger one. But yeah, the technology itself is a water-based resistor jet.
Okay, yes. Yeah, I'm wondering. I'm wondering if the next presenter, Leila Nahiri, is somewhere here, or is somebody knows where the presenter is. Okay, there is, don't. Okay, yes. Then the another question is that is the last presenter in this session Jeroen Vink somewhere here or close, or maybe somebody knows where the presenter is, because it would be nice to have more presentations. But it looks to be that we don't have more presentation in this session. So now we have a break. So let's thank the speakers once again.
Test.
Well, good afternoon, everyone. Now starting in Palaver is a session on planned CubeSat missions. And first to begin will be Martin Starek on a relativistic positioning system for a lunar CubeSat mission, right?
I think I can speak without the microphone, if you hear me. For the streaming. Okay, well then I will use the microphone. So hello everybody. I will now present you the LUREPOS project, the Lunar Relativistic Positioning System, and it's a CubeSat mission to the moon. And yeah, I'm Martin. I worked as a systems engineer on this project, and I'm very happy that I can be here at the Winter Satellite Workshop. Yeah, thank you. Okay, so first a little bit to the background of the project. So LUREPOS was an ESA Phase 0 concept study led by Uroš Kostic. That's a senior physicist in Slovenia and founder of Alta Lab. And it's under the European Exploration Envelope Program, the E3P, which is equivalent to the Terra Nova roadmap of ESA. It's a ESA strategy, let's say, for future robotic and human exploration with the 3 exploration destinations, the low Earth orbit here to the moon and beyond to Mars at some point, right? And we in particular in this project were under the small missions for exploration call. Why is ESA funding these small missions? Because they say it's cost effective, it requires less funding, and it enables more frequent missions, sustaining exploration efforts, and yeah, maybe filling some scientific gaps or technological gaps that are needed for later on larger missions. So a little bit to the consortium. It was 4 countries with the prime Alta Lab in Slovenia and also instrumentation technologies, the payload people, Portugal for the ground stations with Thales, Czech Republic with TRL Space, and Romania with Initium Space supporting the engineering activities. And well, let's get to the mission concept. So what is LUREPOS actually? So first, you know, I said it's the Lunar Relativistic Positioning System. So what positioning system are we using now here on Earth? So we are using GNSS, right? The Global Navigation Satellite System, Galileo for Europe, for example, where we use 4 satellites, get their times, get their positions by a ground station, and determine basically the position of the receiver by quadrilateration of these positions, which is basically that the receiver sits at the intersections of these 4 spheres. However, as I said, we need some ground infrastructure for this, like ground stations, but moving on to the other exploration destinations, maybe we need something else. And the idea that Uroš had for this proposal was to, instead of using the 3 space coordinates and 1 time coordinate, we use the proper times of the satellites in 4-dimensional time space, which analogically to the 4 spheres you saw in the picture on the previous slide, we would have now the light cones in 4-dimensional time space also intersecting in 1 point. These are also called the emission coordinates, since like every spacecraft basically emits a signal that is then connected to the receiver by a light-like geodesic. And now making a step further, not just using 4 satellites, but only 2 satellites, we can have 2 satellites communicating with each other and exchanging timestamps of their proper times. And over several orbits, it would allow the determination of their own orbits. As you can see actually here, the run of the algorithm in a simulation from Uroš. And that means that this concept would enable us to not rely on ground stations on Earth, and we don't need time synchronization. So it's quite easy. The mathematics behind it's hard, but yeah, I'm doing the systems engineering. I wasn't doing the idea. Yeah, and using this concept is perfectly in line what ESA wants us to do, right? To basically put some development that will bring us beyond Moon and to Mars maybe lately, because we don't have ground stations on Mars yet. So the mission objectives, just to sum it up, to implement and evaluate this fully autonomous navigation architecture using this relativistic positioning. And the secondary mission objective actually arose during the course of the study where ESA said, you will have some CubeSats with very precise clocks on board, right? So we can use it to actually calibrate our own infrastructure, which is LunaNet. That's a joint project of NASA, ESA, and I think also JAXA, where I will speak about the ESA part later a little bit. So let's get into the system architecture. Briefly, at the core, of course, of the satellite, always the payload. The primary payload would be the signal acquisition and atomic time-stamping unit, basically a precise atomic clock that would time-stamp the signals, transfer it to our secondary payload, the S-band radio, that would transmit it then to our other satellite, and these exchanges then would allow the onboard computer to run the algorithm on board and determine the orbits of the two satellites. So this is the big picture communication architecture. So this figure, maybe it's a little bit overwhelming, but that's like the maximalist view of this whole mission, where we have our Lurapo satellites communicating with all LunaNet assets. We don't have to go in deeper detail here, but what we were envisioned is that we would use S-band for the time-stamping and the inter-satellite links between all LunaNet assets, according to the LunaNet interoperability protocols. And we would have X-band for the data direct to Earth, the DTE, downlink to basically downlink the data to evaluate it on ground. Now maybe getting our feet on the ground again and zooming out a little bit. The first idea was to have two Lurapo satellites in these orbits here, just exchanging the timestamps and reconstruct their orbits on board. However, ESA is planning to implement their Moonlight Lunar Communication and Navigation Service in the future, which is part of LunaNet. It's quite confusing. And we could use these LCNS nodes to also reconstruct their orbits and have more data and even validate this because they, of course, will know their orbits. Furthermore, we could also use the communication node of LCNS to relay our data back to Earth, not relying only on the X-band direct-to-Earth link for our payload data then. A little bit of a system overview, really briefly. It will be a 16U CubeSat, two of those. That's what we concluded in our study. About 18 kilos, we will have redundant SATU units. We would go with a standard avionics stack, let's say from platform providers that are already in the market and just upgrade it, let's say, for deep space. And we would use electrical and chemical propulsion for orbit maintenance and attitude control. A little bit about the SATU. It's a really nice payload in terms of its low power consumption, small in mass, small in size. So that allows actually that we can use only a 16U, which is maybe not possible for other missions that are going to the moon, like let's say mapping missions, right, that have to implement a big optical payload. So I'm saying here, okay, it's a simple CubeSat, right? But why it's not simple? So maybe you think about CubeSats, about large constellations in low Earth orbit, about student satellites being launched, right? But the lunar environment is unfortunately not like the low Earth orbit and maybe the commercial of the shelf components. Not maybe, but they are definitely not ready for the lunar environment. So a lot of the budget goes to basically upgrading these components that are readily available on the market to do the radiation testing and prepare them, let's say, for the lunar environment, also the other thermal environment there. And what was also a huge problem was the compatibility with the Moonlight LCNS, because ESA is still developing that. So they were doing their huge iteration loops, and we were doing our iteration loops, and then at some point, you know, they were always saying, you have to go to different orbits, which is not what we are used to, because we are, let's say, just taking the inputs from ESA that are already there, and we are usually not, dealing with these dynamic inputs from ESA. What also is a problem is to get to the moon, actually, right? I mean, there's not much flying there right now. We talked with Firefly Aerospace, landing the Blue Ghost there, and we hope that in the future there will be more launch providers that will be readily available to give us a ride share to the moon, right? So if you know anybody, just let me know. Because just going to the low Earth orbit and then using maybe a kick stage to propel yourself to the moon would be maybe possible, but we basically said that it would be too risky for us for this small mission. It's a 16U, right? So I mean, it would need to survive harsh transfer there. So, coming to the result, I will sum up this horrific amount of text in a few words. We can't do the mission objectives. So we said it's possible to actually be the enabler for the calibration of future infrastructure. We could play a crucial step in the next steps to moon and beyond. And what was for ESA also important is we can go for a 2030 launch, which is independent, let's say, of the timeline of Moonlight LCNS. Because the Moonlight LCNS timeline is being shifted, and we wanted to not rely on that. That's also why we have like this independent X-band direct-to-Earth link. And we stay under the 15 million euro, mostly due to the simple nature of the payload. And there's also other possibilities, not to use 2 satellites, but maybe even just build 1 satellite and implement our SATU payload as a secondary payload on another mission flying to the moon, like maybe the Twardowski mission from Cryotech. So that's all still in the stars. And yeah, I hope that we will move on. And yeah, that's it. Please visit Euro's website, AltaLab. He has great stuff besides relativistic positioning. And yeah, that was 12 minutes now. So I think there's enough time for questions. Yeah, please.
Okay, thank you for the presentation. I anticipate that I'm not expert in relativistic positioning, but I remember from my colleagues when we used to work on that, that they told me that you need at least 3, if not 4 satellites, and 2 are not enough. But I think that you are looking at orbital trajectories. You claim that working on orbital trajectories and not generic space trajectory, 2 satellites are enough for full positioning?
Well, the thing is, 2 satellites are enough to create a reference frame for themselves, but you have, for example, no absolute position in terms like to a location on Mars. So that's the problem, let's say. You know where they in space relative to each other, but that's basically it, right? Because you're still lacking, let's say, another component like the 3rd satellite that would position it. But this would be, let's say, the first step of evaluating this. Of course, in the later steps, you could implement 4 satellites to have really an absolute position.
I can ask you one more question. I also remember that they were telling me that in using relativity positioning, you were not allowed to use propulsion because it was affecting with relativity. The satellite had to operate just in free space and no external force. Can you still operate having thrusters on board or not?
Well, we can operate with thrusters on board, but we can't do time stamping, like measuring the times, the oscillator, while thrusting. That's something that you can't do because really you have these disturbances, right? I mean, you have the disturbances by the inhomogeneous gravity field of the moon, which is inherently basically in the equations, but you have to really freely fall through your geodesics in space and not thrust, yeah. But that's not a problem because the orbits are allowing you to be a long time in orbit without any thrusting.
Right, thank you, Martin. Thank you for the questions.
Yeah, thank you. Just if I can say something, if you have questions, please just scream Martin on me then in the hallway, yeah? Thank you.
Yes, after the session, thank you. Next we have a concept, or a mission concept on orbital docking nexus by, was it Nishant Pushparaj? So, if you are here, step up to the stage. So, this seems to be a remote presentation. When you're ready, Nishan.
Hi. Can you hear me okay?
Yes, we can.
Hello, can you hear me?
We can hear you fine in the session hall.
Hello everyone, can you hear me? Can you hear me? Hello, can you hear me?
We can hear you fine at the session hall.
Hello.
We hear you fine.
Okay, sorry, I just saw the message. Good afternoon, everyone. I'm Nishan. I'm an assistant professor at the University of Nottingham, UK, and this work is in collaboration with my colleague Chantal Capelletti. We both co-lead the space lab at the University of Nottingham called North Space. Today I will be presenting on the mission concept of something called Orbital Docking and Integration Nexus, or ODIN. Thank you for the opportunity for me to given to me to present online, and thank you for your patience, and thank you for attending this session. The importance of this topic is because that the access to microgravity and space environment remains scientifically invaluable, because you have all these microgravity experiments that's currently being done in international space stations, or something that will be because we no longer have issues with having more launches, but then again, it's up to hosting and operation is the key issue right now for all the small industries or universities and small research groups that's working on all these microgravity environment experiments and things like that. What happens when ISS is no more? And so, as you know, that ISS will not be in orbit forever. And what happens to these small microgravity experimentations and things like that? So obviously, we can't be sending an n number of CubeSats in space to deal with these experimentations for quite a long time. The key idea is we don't have an infrastructure that that can enable the continuity of the orbital research in post-ISS era. In order to tackle this, we were thinking about a 27-unit CubeSat. It's a reusable platform designed to host CubeSat class payloads between 1 to 3 unit in size, but not just one. You can have a maximum of 3 of these 1 to 3 unit size can be hosted in this a bus. So this spacecraft provides basically power, data handling, thermal management, and attitude stabilization, and all end-of-life disposal all in one place. So the key idea is that the teams or the industries who are working on any experimentations or any payloads doesn't have to focus on the longevity of these experiments in space, or how to collect the data and how to transmit the data. So all the companies and the universities can only focus on making the payloads, whereas this system can dock with the payload. And I'm quickly explaining the concept of operations about this. So this orbital Odin will be in orbit, launched separately, and then it has its own ADCS and all the subsystems within itself. And the key idea is that the payloads that needs to be docked to this system can be randomly deployed at any point of time, can have 3 or more, 2 or more, maximum of 3 CubeSats can be deployed at random locations. So this orbital Odin can reach the defined CubeSat and dock it with itself. And the initial idea was to have these CubeSat payloads can get inside the body of the actual 27 unit itself, but then we looked into the feasibility and the reliability of these systems, and we understood that it's not possible. For a small scale case study, we used a one single 1 unit and a 2 unit CubeSat to be docked at the same time. So in theory, we can have two experiments can be done simultaneously in one system. And for better for initial phase, like we have only the translational motion that you can only change the altitude but not the inclination. But in the future, we might able to look into feasibility of having out of plane and all that. So finally, one of the key important aspect of this concept is that once the mission is complete, so basically, typical 1 unit CubeSat can have a limited time duration to perform experimentations. But within this, you can increase the longevity of the experimentations to the desired number of years or months that somebody wants to do it. And once it is done, it doesn't stay there forever. So the system can undock these satellites and then naturally deorbit those 1 to 3 unit payloads, but the actual host will remain in the orbit. So you can keep reusing this as long as it is possible. But in the feasibility study, we realized that we can have maximum of 3 cycles that can be done to host it perfectly, and then once by this project itself, like can deorbit at the end naturally. So this was developed currently through structured systems engineering approach. We also performed some resilient systems design to these concepts, and then as you can see, it usually was following all these mission concept reviews, and we have made some mission requirements and systems requirements that we recently published about this work. And the key aspect about this system is that the core subsystems is all off-the-shelf components. So the only things that we are worried about is these specialized subsystems. For example, if you require the 1 unit or 3 unit payload that needs to have a dedicated environmental system, this is most specifically for the biological payloads, so they need a separate temperature and lighting conditions. Then that is a different subsystem that might require for such missions. So this will allow enable can act as a hosted system that can host these CubeSats to perform. And in particular, we have simple docking mechanism that uses just iris mechanism. It's mostly, we don't want to use more complicated robotic arm on complex manipulators. So it's simple, but then again, like electrically robust. So this is just to illustrate like how this is going to work. So you can have so here in this example, we used one of our payloads called Vita. So this is a project where we plan to grow protein in space. And we work on this in partnership with the pharmacy department at the university. So this Vita, I mean, we have more information about this Vita, but the whole idea here is that in case if the Vita is launched like this, and then the hosted satellite can match with the attitude of the 2 unit CubeSat, and then it can dock within itself. And once it is done, you can see the Vita's cross-section view. So it can connect with the data and power connectors, and then also seal properly with the mechanical connectors as well. And so we've been currently working on the rendezvous and approach related studies. Mostly we would like to extend this to more autonomous system in the future, but again, like I said, like at the end of the experimental life cycle, the Odin supports controlled undocking, and this payload can either be released for independent deorbiting or can remain docked and finally perform the end of the life disposals. And therefore, this ensures the responsible orbital behavior and satisfies sustainability requirements. for deorbit mitigations. And in our case study, we were using these two examples. So one is a 2-unit experimental CubeSat, which we call Project WIDA. It's a 2-unit. And initially, this was selected as Orbit Your Thesis competition by ESA to put it in ISS. But unfortunately, we passed the PDR, but then we have some issues with the pharmacy team to develop these protein and synthesis, and we were not able to continue with it. And in the future, if we would like to run this test case scenario, so we thought that we can use this Project Beta's case. So this Project Beta, in order to conduct this biological experiment, we would require a power of 34 watts and at least 1.4 gigabytes of experimental data, and which this Odin can support this autonomously. And also, finally, the AstroJam is another project that we applied for or flyer thesis completion. But then again, currently we are developing this as a 3-unit CubeSat, which basically the idea is to map the GNSS interferences across the globe, and it's a small payload. But then again, the idea here is that a single Odin can have both of these payloads docked in one system and can have a biological experiment at the same time, and also can run a GNSS interferences mapping mission at the same time. So basically, just to summarize, the idea of Odin is to have a mission-class orbital infrastructure that extend CubeSat scale research beyond disposable platforms. And finally, the point of this is to reduce the barriers to entry to space experimentation directly after the ISS era. And most importantly, the Odin enables payload teams to focus only on the science and technology development, while the platform handles the spacecraft operations. So when it is done, the aircraft, the spacecraft can deal with all the attitude adjustments and all this, and the science and technological team doesn't have to focus on the main operations. Thank you for listening, and I'm happy to take any questions. So this is our contact, and we also have some first IAA Plan 3 workshop happening at Nottingham. If you're interested in this, please feel free to look into this.
Thank you, Nishant. Let's see if did Zoom just crash there, or Zoom quit unexpectedly. But maybe you got a little bit of time to think about good questions. We'll at least try to relay them over the chat. Okay, we see the session still running. So can we hear just right in the chat? Okay, can you hear us, Nishant? I don't think he can still hear us. So any questions? We will relay them through the chat if need be. All right. We send our thanks to Nishant, and up next we have a mission concept for radiation belt studying with very low frequency wave injection with a tandem CubeSat mission.
Good evening. I will present Lucibus, which is basically a dual CubeSat dual CubeSat mission concept about injecting VLF waves into the magnetosphere and observing the potential changes in the particle distribution due to this VLF injection. The motivation behind the work is basically a long-standing, let's say, experimental gap in magnetospheric physics in general. and namely the lack of co-spatial and co-temporal observations of particle and waves. So some some basic introductory concepts to understand the mission concept. So the particle of a trapped motion, the motion of a trapped particle inside the Earth's magnetosphere can be broken down in three individual motions, namely the gyro motion, which basically is a gyration around the magnetic field line, the bounce motion, where the satellite is mirrored between latitudes at the northern and the southern hemisphere, and the drift motion, where the orbit is drifted around the Earth. With each motion, there is a value that is preserved, namely the adiabatic invariance. Also, its motion, and that's the key for the Lusipus mission, is that its motion is characterized by a specific range of frequencies. Okay, thank you. Yes, also in the same region coexist a large number of waves with different frequencies and different propagation characteristics. And the important thing is that when a specific wave, the frequency of a specific wave matches one of the frequencies of each individual motion of the particle, we have a resonance condition. So we have a gyro resonance, a bounce resonance, and a drift resonance. Lusipus will focus on the gyro resonance case, where we will focus on the interaction of electrons with VLF waves in the range of about 5 to 30 kilohertz. So, wave-particle interactions in general are well described theoretically. There is a lot of theoretical work over the past decades, even from the 60s. But the problem is that direct experimental validation and quantification of the interactions is still lacking. So the main problem is that most missions measure waves or particles, but not both together, at different locations or times. So the results lead to correlation rather than causation. For example, on the upper right corner, you can see a magnetic conjunction between the DSX, where DSX was one of the, basically the first spacecraft who tried to inject VLF radiation inside the magnetosphere, and Arase, which is a well-known spacecraft for measuring particles. So this, on the upper right corner, is a simulation that we did for a conjunction between the two. The blue lines represent the transmission of DSX, basically inside the plasma, inside the magnetospheric plasma. If you try to inject radiation, the radiation will be confined in a cone, the so-called radiation cone. So our goal is to move from passive observations to basically active and control experiments. So by injecting VLF waves into the magnetosphere, we can track the observe the direct particle response, so we can directly connect the cause and the effect. And basically, we can use the magnetosphere as basically a lab, a natural plasma laboratory for the interactions. So the concept right now is about two CubeSats, two 6U CubeSats. One would be the transmitter satellite and the other receiver. The transmitter satellite will carry as main payload a VLF transmitter, which is a rotating magnetic field source, and a Blackberry probe to characterize the plasma conditions during the transmissions. And the receiver satellite will carry instruments to measure the magnetic and electric path of the wave of VLF waves. and a particle detector to measure, try to find energy, changes in energy distribution of the electrons. The observation scheme, we currently focus on two schemes. In the first one, we have the two satellites. Basically, we aim in control and repeatable magnetic conjunctions between the two satellites. So in the first scheme, we have the two satellites in the same orbital plane, and we could have conjunctions when the one satellite is north and the other is southern of the magnetic equator. On the second concept, the receiver satellite can be in a low Earth orbit, around 2,000 to 3,000 kilometers. And again, we could have magnetic conjunctions when the two satellites are in a similar way like the one presented. So the primary objectives will be to demonstrate efficient space-based VLF injection, especially from a small satellite like a CubeSat. Secondly, to characterize the wave propagation, and this will also help ray tracing techniques inside the magnetosphere. And thirdly, to investigate wave-particle interactions. So the key scientific question would be to how does the injection propagation of VLF wave packets depend on the plasma environment, which is quite open issue right now. What are the spatial and temporal characteristics of artificially injected and natural Whistler waves inside the magnetospheric plasma, and how do VLF wave packets influence the pitch angle distribution of resonant electrons? So where we are at now? Right now we are in the mission definition part of the mission. We have set up a full mission simulator where we have different modules. One is the WIPIT, which is also published online. It's an open source tool. You can find it in GitHub, which is basically what WIPIT does is to quantify interactions between electrons and different kind of waves, Whistlers, which is directly related to Lucipus, but also MIC waves and other. We have also a module about the orbital design of the mission, basically to find magnetic conjunctions. We also have a module about the simulation of the coupling of antennas inside the plasma, which is really interesting and it's the main difficulty of transmission inside the plasma, the magnetospheric plasma. And then finally some modules which are used to define the parameters of the payloads of the two satellites. So the key result so far is that simulations indicate measurable scattering signatures at the typical magnetospheric conditions. So it's hopefully it seems that the whole concept could work. So to sum up, wave-particle interactions remain a key unresolved problem, and especially their quantification. So Lucipus aims to be the first control in situ wave-particle interactions experiment and to enable controlled cause and effect measurements. And the dual CubeSat architecture closes a critical experimental gap. So to sum up, I could say that Lucipus turns wave-particle interactions theory into a testable space experiment. So, thank you for your attention.
Thank you for the talk, very interesting. It just seems that the spacecrafts will be in like challenging particle environment, right? So I would like to ask, what implication does it have on the mission lifetime of the mission and maybe on your, let's say, radiation hardening of the components?
Yes, of course, radiation hardening is one of the main risks of the mission, and we're currently working on that. I don't have some solid answer on that. It's basically something that we are looking into right now during the mission definition phase. But yes, it's the main issue, especially when we aim to operate at least the transmitter satellite at L2, the magnetosphere. It's basically almost inside the radiation belt. So yeah, that's a very critical point of the mission.
Okay, that's good to know that somebody is going through this trouble also, so maybe we can...
Yes. So the lunar...
Other questions?
Thank you for the very nice talk. I'm just interested in which frequency range are you interested in measuring for this VLF waves in terms of magnetic fields?
Okay, basically we aim to inject whistle waves, and in order to have waves that can interact with a gyro resonant concept with the electrons, we aim to 30 kilohertz is the range that we could use. Now the simulations mostly aim at around 20 kilohertz.
Okay. So you probably use a search coil magnetometer for that. Okay, thank you.
We still have time if there are more. If not, thank you, Stelios, very much. Next we have Kristin Kandelin to present the SUTS Estonian CubeSat project and its current progress.
Hi, once again, I'm Kristin Kandelin. I'm the lead systems engineer for the SUTS project, and I'll be giving a sort of, I guess, progress update about the development of the satellite. So first of all, before SUTS, we've had 4 student satellites in Estonia. They've been individually developed by universities, so TalTech and University of Tartu, but we decided to come together, and from this, Estonian student satellite was born. So what is our mission? Our mission is to increase the expertise of this generation of students, and also by that give the space sector some a boost. And how we do this? First of all, we're obviously developing satellites. We are also popularizing science by being at various events and speaking out about what we do. And we also cooperate with various companies in both public and private sector. But going back to SUTS, so what is SUTS? SUTS stands for Strategic Updates Testing Satellite. I know we talk about CubeSats in this section of the conference, but I'm going even smaller. This SUTS is a 3P pocket cube, meaning its dimensions are 5 by 5 by 18 centimeters. It has 2 payloads. It has the encrypted optical communication module, which you can see actually here. And the moon regolith simulant solar cell, which is on the other side of this panel in the back. And it is scheduled for launch in 2028. So what is the goal of our mission? So first of all, as we are a student organization, our goal is to give practical experience to students. We also want to provide a platform to our payload partners, which are Kolberg Space and Scudo for the optical communication payload, and a PhD student in Taltech for the moon regolith solar cell. And lastly, we want to encourage cooperation between various Estonian universities and schools. So before I go on, I want to go over what is inside SUTS. First of all, the central part of SUTS is the command and data handling system. It takes care of all the data management and tells everything what to do. Then we have the communication system, which takes care of transmitting all the data to the ground stations. We have the attitude control and the determination system, which takes care of the pointing, the electrical power system, and the payloads. And this is all encased in the mechanics and the mechanical body. Today, I'm not going to go over everything. I want to talk about the attitude control and determination system and the electrical power system specifically. So first of all, attitude determination and control system, in short, ADCS. Why this is so important to us is because we have an optical communications payload, which has placed us in quite strict requirement area. We have to go for 5 degrees absolute and 1 degree relative pointing accuracy. But this is quite complex for us. The ADCS team also managed to create a very nice simulation environment in Python during this last year, which features the tumbling simulations. So when the satellite exits the deployer, it is spinning very fast and it has to detumble. And also they have made quite good simulations about nadir pointing, so pointing towards our ground stations. What is also interesting is that we are doing our own magnet torquers. Here you can see an image of the winding process. It's our engineer has a good patience, let's just say. But onwards to EPS, or electrical power system. Why I want to talk about this is that it has quite a compact design. You can see that everything from battery charging and solar panel management, and also the voltage regulators and power switches is put on one 46 by 48 millimeter board. We also have a very hot redundant design, meaning we have multiple independent maximum power point trackers, or MPPTs, and also multiple voltage regulators, meaning if one regulator fails, we still have one for backup. What is also special is the fact that we don't really have a separate battery management system. It is actually managed by the MPPTs, so we do not have that extra complexity. But another thing I want to talk about is what actually changed during this last year. We started last year, we had this design on the left. We had 3 deployable wings. Then at one point during summer, we realized that we don't really need the 3 deployable wings, so we removed a pair. It got a little less complex. And during winter, we had an issue, so we had to change the opening of the optical communications payload, which used to come out from here to here. And through that, we also changed the antenna design. So as we're a student project, with every student project comes its own challenges, as we're not that experienced. With every student project has a problem. One common problem is the high student turnover. We have students learning, finishing their bachelor's or master's, then they are moving on. We have lost quite a lot of good engineers, or the engineers just lose interest because, yeah, it's voluntary. They might have some better ideas of what to do. This also, we have had some organizational problems. For example, off the top of my head, we have had problems with our financial situation, although this has been mostly fixed. But lastly, one of our more severe problems is that we, like during our years, we have lost a partner. We originally had 3 partners. This was largely due to communication problems. We've had long response time from partners because we might not be their main project, so we have a priority for our mission, but they don't really prioritize ours as much as we do. And also misunderstandings. So as I already spoke about this, but at the start, the optical communications payload opening was supposed to be on the smaller side of the satellite, but they misunderstood somewhere along the way. Even though we had it marked down in the requirements, we had shared them. We shared them. We gave them the requirements, but during one meeting, we suddenly realized that they had put their opening here, so we had to quickly change the design. So in the future, we will try to be even more precise and check with them if everyone has understood correctly. But I have talked about the past, but what is next? So for those who have already been involved, those already know, but we are pushing to finish the engineering model for the satellite by the end of February. After we have done that, we are planning to do a testing campaign, which will hopefully end with autumn or a bit later. So that means we will be conducting environmental tests, shock, vibration, thermal vacuum, and some functional tests with the satellite. And after that, hopefully, it will be onwards and upwards with the flight model development, testing, and launch is planned for 2028. Thank you.
Okay, thanks for the talk. You are doing really cool stuff there. I have actually 2 questions. So maybe the first one is, could you describe the optical communication payload a little bit? So is it a transmitter, receiver, or like, who are you communicating with?
So I don't really know the specifics because it's an external party payload, but basically we are just transmitting as far as I am aware. Yes, confirmation.
Okay, and the follow-up question, you said so you collaborate on this like the universities of Estonia basically.
Mm-hmm.
So how are you managing that? Like you are doing Zoom meetings or you are doing like weekend workshops, like, because that's quite challenging, right?
Yeah, actually both of your like endings of the questions were correct. We are both on site and hybrid. So we have like work weekends. We actually just had a work weekend. So then during the summer we have like work weeks, but the towns themselves try to cooperate as much as possible, and once in a while we try to come together. So yeah, it is challenging, I have to admit, especially when like teams are divided by like towns. But we are managing.
Okay, that's nice to hear. Yeah, thank you.
Any other questions? Ooh, 2.
Thank you. Yeah, thank you for a very interesting talk. You mentioned from universities and schools, and I think I've heard that maybe some younger students have been involved. Can you elaborate a bit on to what extent and how that's gone?
So there are even a few of those people who used to be high school students and in the organization in this room, but these are mostly from like high school level. We don't really go to middle school because that's too young, but well, we've had like actual like electronics people, of course, or like actual like technical people as well, but there have been like roles with every like we have had communications people in high schools as well. So yeah, if that answered your question correctly. There was one more.
The CubeSat has already become a standard. Do you think that also CubeSat will soon become a real standard for small satellite, very small satellite?
Do you mean to say that? So, oh yeah, picosat. Do you mean picosats or? Can you elaborate? Okay. Well, I would say it's a real standard in that sense, or because there have been around 100 Pocket Cubes already launched, even though it's a smaller community, but it's growing. Yeah, I don't know.
Thank you very much, Kristin. I don't think we have any more questions. We're in good time. And next we will have Augustinas Rukas presenting Aalto 3 mission concept and the framework overall around it.
Boop boop, test test. All right, so hello everyone. I'm Augustinas Rukas, the system engineer and project lead of Aalto 3, our next generation CubeSat project at Aalto University, long awaited. And this is Slavena, our structural engineer. So today we're going to talk about what Aalto 3 mission is about, what kind of goals we have. We're going to look a bit into our subsystems, and I'm essentially going to try to justify for you guys why we're not only building a generic CubeSat mission, we're also building a framework for future student space missions at Aalto and maybe other universities. So why we're building a capability. A little bit about the history of Aalto satellites. So Aalto 3 is going to be the third satellite of the Aalto lineup. We've been kind of reversing in size order here, interestingly. So the first one was the 3U, the second one 2U, now we're going to 1U. I was also joking about how maybe Aalto 4 will be a pocket cube, and then maybe we'll have something smaller, but for now 1U. We also have a couple of for-sale satellites launched, which is a parallel lineup of more scientific satellites made at the same lab by researchers. And also want to shout out the Aalto Space Association for a little bit, because most of the people in the Aalto 3 project are from the Aalto Space Association, so we're also helping to organize this conference, and we're trying to build a new hub for space students in Aalto University and also centering on Finland. Right, so Aalto 3, this is how it looks right now. It's a 1U CubeSat, has a couple of antennas, but we'll get into the technical details very soon. Here is a bit of lore, a bit of backstory about the project. So the project actually started in 2017, which means technically it has been going on for, well, 9th year now. Because of COVID and because it's a student project, student run, mostly volunteer run, It dissipated in COVID. There were a couple of tries to revive it. We call them iterations. Right now we call our iteration Alto 3.4. We started in 2024 October and have been working ever since, and we're on track to completing our engineering qualification model fairly soon, next couple of months, and I think we're on track for launch. There have been quite a bit of contributors in this iteration as well. We have had over 30 students participating in the project, and most of them have actually been bachelor students. We have master students as well, no PhDs, so very accessible, very education-oriented, and as long as people are motivated, they have a tiny bit of technical skill, we let everyone contribute and learn. So we have we're trying to produce the next generation of students in space technology as well, along with our courses. Now let's get into the mission objectives. So first of all, of course, you want to build a 1U CubeSat, which puts a lot of constraints on us. Power, size, mass has been pretty fun, budgeting and getting around all of those. And we also want to have a capability for 1U CubeSat, so build a framework of them at Aalto University, because they're cheap to make, cheap to launch, and if students want to iterate on future space missions, this is going to be their best approach. We have something called MIRA, which is a scientific instrument, which is a dosimeter radiation measurement instrument from the University of Turku. They're making it, and our main goal with it is to investigate the South Atlantic Anomaly region, which is a magnetic anomaly that occurs because of the tilt of the Earth's magnetic axis, which causes the inner Van Allen belt to move closer to the Earth, and therefore we have more radiation, so more energetic particles at lower altitudes there. And we're trying to look into that, and also do some global measurements too. We're also testing some of their tech, so they have some new interesting FPGAs there that we want to test out. Next is some technology validation. So we're actually developing a whole S-band subsystem in-house, antenna, transceivers, everything. So we are building that capability too. We're going to test it through our 1U CubeSat. Even though our primary communication method is the ultra-high frequency, we want to make sure this works for our future missions, and Alpha 3 is going to also be used for this. We want to also validate GNSS capabilities in orbit, so we have a GNSS chip that we're going to have on there, and also just making sure that for future we have the capability to use this. It's also going to be used for very accurate data mapping to location for our radiation measurements for the MIRA instrument. Next, we want to capture photos of the Earth, because why not? We have a Raspberry Pi on board. It's going to be pretty fun watching our satellite actually work, something visual, something fun, confirm that it's working. And also we want to provide learning experiences. So as I mentioned previously, this whole project is also about education, building the next generation of space-capable students, and I think we've been doing a pretty good job at that with many contributions and more people joining as well. This is our product tree. It's pretty generic subsystem-wise. We are going to dive into them one by one shortly, but yeah, essentially we have our own ground segment as well, and we're also going to be using the SatNOG's decentralized ground station network for beacons all around the world. For the avionics stack, we are iterating on the previous Aalto and 4-cell missions. So we've been upgrading our avionics stack ever since Aalto 1, and with each mission is getting better and better. We're also adapting it to our mission requirements and 1U CubeSat constraints, so making quite a bit of modifications, but drawing from the same flight heritage and developing it even further. Passive attitude control, this is also something I'm responsible and leading. We have opted for passive control because of our power budget and our power constraints. Being a 1U CubeSat, only 2 power cells per side on average. We generate, while in the sun, around 1.8 watts. So that's in an orbit an average of 1 watt, not much to work with. So magnetorquers, reaction wheels, not really a good option here. We also don't have very strict pointing requirements, only for the camera. which we can meet by having a permanent magnet that aligns us with the Earth's magnetic field vector. So we know where we're kind of pointing at a given location. And we're also using hysteresis rods, which are soft magnetic rods that, while the satellite rotates, they get magnetized in different directions. Magnetic hysteresis happens, energy is dissipated, rotational energy is converted into heat, and therefore our satellite slows down after getting deployed. So we detumble, lose much of our rotational kinetic energy, align with the magnetic field vector, and we have a fairly stable satellite. And now Slavena is going to talk a bit more about our structure.
Thank you. So, as Augustinas already mentioned, one of the main objectives of this project is to be a learning experience for students. So, our main vision actually for Auto3 is for it to be an EduSat, which means that it is not just another student project, it's a framework, a basis that future student projects can use for their own mission objectives. How we are doing this is through our structure design. So when future students come into uni and they want to build their own satellite, they already have the structure, which they can utilize for their own mission objectives. It is very modular, very easy to, can very easily be adapted to certain instruments that you might need. Just for an example, our hysteresis mount was changed a few times already. What this actually allows you to also do is, or allows students to do, is see problems that might not be easy to see in the beginning, but then might occur in the future. So that helps prevent that. Also, our budget is not that high since this is a student mission. And we are also utilizing off-the-shelf components. So this project is super accessible for bachelor students, for master students, for everyone. And it can also be utilized in courseworks and project works. Another example of learning objective that we have here. Yes, so one thing that we are learning about right now is solar panels, and we are trying to kind of do something that's different, that was not done in the first satellites before. So we're trying to test two different methods, gluing and soldering. That is actually because we want to see what actually happens when we produce them in-house, like how do they pass our tests? What is a better solution that we can actually then send to space? So this has been a great learning experience. Also, the people working on the solar panels right now are mechanical engineers who might not even know that much about soldering, etc. So it's great for everyone to learn new skills.
Thank you, Slavena. So yeah, as we mentioned, we're both building a satellite that has lots of cool stuff, that has many payloads, kind of overloaded for a 1U. I think I haven't seen much missions that are testing this many things and have this many instruments on board. We are also building a capability, as Slavena mentioned, for courses. So the EduSat concept is designed so it's very cheap to machine, very easy to switch out different payloads, have different configurations inside. So students, satellite systems courses, for example, can build their own CubeSat. We can have different PCBs, different payloads, and people actually learn how to assemble these things, how they look. So education, cool mission, platform for the future. This has been Auto3. Thank you very much. Any questions?
Okay, thank you for the presentation. Just one question. You just mentioned the solar panels, solar cells. I think that you want to see whether to either solder or glue in them, but I think you have to do both of them. I mean, can you just either or soldering or and not both of them?
Yeah, so we're testing whether it's better to actually solder the solar cells or glue the solar cells specifically to the solar panels. It's easier to have a method with soldering because it's easier to for students to assemble. You don't have to mess around with glues. You don't have to worry about air bubbles. It has its own caveats. For example, okay, what's going to be the expansion of the solder when your cell is getting hot in the sun? That's why we want to run it through TVAC tests. We don't know which one we're going to go with in the finale yet, so we're just seeing like if it's worth to go with the messy gluing method or do we opt for something that's solderable. Yes, I mean on the solar panel, those components, yes, but the actual solar cells, the main part. Thank you.
Since you have so many payloads, what is your weight of the 1U?
Oh, we fit under 1.33 kilograms. With the new solar panels coming, we need to redo the mass budget, but we're more worried about the power budget instead because, okay, how are we going to do the cycle of those payloads? But mass, we actually fit.
So you're talking about building a framework, but so far you've only talked about it as a technical framework. Are you also building a management and a workflow framework as well? Because I find that this is one of the big problems with student projects is inexperience with workflows and project management.
Very good question. I love that question. Yeah, I mean, student projects are student projects. Students get bored, students get hired, students graduate. It's especially for salaried projects, which sometimes take years. We took 9 years. Yeah, we're trying to improve, for example, the way we document things. When we came into the project after previous iterations, we were left with a mess essentially. We wiped everything clean, made a new structure, also trying to manage the project well. We're using, for example, project management tools like Linear to make sure that, okay, people in different subsystems know what's happening, what's doing. We're trying to have frequent meetings and for example, me as a system engineer, I'm always trying to bridge people, inform them what's happening in other subsystems. So essentially, clarity of the project, better documentation, and yeah, it's been going well so far. This
I have a quick comment / question about you mentioning the mass budget being like close to the limit, but for years, some years already, CubeSat is 2 kilo standard. So what have you thought about just going to 2 kilo mass budget?
We haven't thought about that. We're trying to stay under 1.33. Thank you very much.
Thank you, Augustinus. Very comprehensive presentation. This was the final talk of this session. Thank you all for your interest throughout the day. Be sure to go up to the expo and the poster session upstairs and join us for the evening program, first at Dipoli and then at Laude Sauna, organized by Auto Space Association.
It was really good.